Welcome, fellow dreamer. Tonight, we journey through the ancient story of metallurgy, from the first spark struck on copper ore to the closely guarded secrets of steel that built empires and changed our world forever. Did you know that Tutankhamun was buried with a dagger forged not from any earthly metal, but from a meteorite that had fallen from the sky? This tale unfolds with soothing music and abstract imagery, gently uncovering little-known wonders and fascinating stories to feed your curiosity as you drift toward sleep. So take a deep breath, sink into comfort, and let your mind and eyes rest as the story begins. The human story begins in a world of stone, wood, and bone, long before the first spark of metalworking illuminated the darkness of prehistory. Our ancestors shaped their existence with the materials that lay readily at hand. Rivers offered smooth pebbles perfect for grinding. Forests provided branches that could become spears or digging sticks. The bones and antlers of hunted animals transformed into needles, scrapers, and awls. For countless generations, stretching back into the mists of time, these were the substances from which all human technology emerged. Picture, if you will, a landscape untouched by industry, where the rhythm of life moved with the seasons and the migration of game. In this ancient world, a skilled craftsperson might spend days searching for exactly the right type of stone. Flint, obsidian, and chert were prized above all others for their unique properties. When struck at precisely the right angle with exactly the right force, these stones would fracture in predictable ways, creating edges sharper than any modern razor blade. The knapping of stone tools was humanity's first technology, and it was far more sophisticated than we might imagine from our modern perspective. The makers of stone tools possessed an intimate knowledge of their materials that would impress any contemporary craftsperson. They understood that heat could alter the flaking properties of certain stones, making them easier to work. They knew which river valleys yielded the finest obsidian, and they could distinguish between dozens of varieties of rock by sight and touch alone. A well-made hand axe represented hours of patient work, each flake removed with careful deliberation, each edge shaped with purpose and intention. Yet for all the ingenuity invested in stone tools, they possessed inherent limitations that constrained human possibilities. A stone blade, however carefully crafted, could not be resharpened indefinitely. Eventually, it would grow too small, too thin, too fragile to serve its purpose. A broken axe head meant starting again from the beginning, searching for new raw material, investing fresh hours in the patient work of shaping. Stone tools could not be melted down and recast into new forms. They could not be bent without breaking or joined together, except by the most crude lashing techniques. The wooden implements of this pre-metallic age have largely vanished into the earth, decomposed and forgotten, but we know they formed an essential part of the toolkit. Spears for hunting, digging sticks for finding roots and tubers, containers for carrying water and gathered foods. Wood offered flexibility that stone could never match, yet it too had its constraints. It could rot, it could burn, and it could be gnawed away by insects and weather. A wooden spear might serve well enough for a season, but it would never become an heirloom passed down through generations. Bone and antler filled certain niches that neither stone nor wood could occupy. The makers of the Stone Age fashioned these materials into needles fine enough to sew fitted clothing, fish hooks capable of landing substantial catches, and ornaments that hinted at the symbolic thinking emerging in the human mind. Antler, in particular, proved useful for tasks requiring material that was both hard and slightly flexible. Yet these materials too came with their own limitations, available only when animals were hunted successfully, and always in shapes dictated by the anatomy of the creatures from which they came. Living within these constraints, human communities remained relatively small and scattered across the landscape. Agriculture, as we know it, could not truly flourish with Stone Age technology alone. Clearing forests required immense labor, with stone axes that dulled quickly and broke unexpectedly. Harvesting grain with stone sickles was possible but inefficient. The construction of permanent settlements remained a challenging proposition when every building material had to be gathered, shaped, and assembled, using tools that wore out and could not easily be repaired. Warfare in this era, while certainly present, remained limited in its scale and destructiveness by the available technology. Stone-tipped spears and arrows could certainly prove lethal, but they required skill to use effectively and significant time to manufacture. The idea of equipping large organized armies with standardized weapons lay far in the future, awaiting developments that the people of the Stone Age could not yet imagine. And yet, even in this world before metal, the seeds of change were present in the earth itself. Scattered across the landscape in certain favored locations lay deposits of materials that would transform everything. Bright green stones of malachite caught the eye with their vivid color. Heavy, reddish rocks of hematite and other iron ores lay waiting in river gravels and rocky outcrops. In a few rare places, nuggets of pure copper, gold or silver weathered out of their host rocks, gleaming with a luster unlike any common stone. For the most part, these unusual materials went unnoticed, or were valued only for their beauty. A piece of native copper might be collected as a curiosity, admired for its warm reddish color, perhaps traded or kept as an ornament. The idea that these strange stones could be transformed through fire into something entirely new, something with properties that would revolutionize human existence, remained undiscovered. The world of stone, wood, and bone was not a primitive world in the sense of being simple or unsophisticated. The people who inhabited it possessed intelligence equal to our own and had developed complex languages, rich cultures, and intricate understandings of their environments. They created art that still moves us today, from the painted caves of France and Spain to the carved figurines found across Europe and Asia. They developed trading networks that stretched across hundreds of miles, established seasonal gathering places, and passed down knowledge through oral traditions that preserved essential information across generations. But it was a world fundamentally limited by its materials. Every task required more time, more effort, more human energy than would be necessary once metalworking emerged. The population that the Earth could support remained constrained by these technological limits. The complexity of the societies that could be organized and sustained faced inherent boundaries defined by stone, wood, and bone. As the last ice age gradually released its grip on the northern lands, as climates shifted and new possibilities opened, humanity stood unknowingly on the threshold of a transformation. The discovery that would change everything lay just ahead, waiting in the ashes of ancient fires, ready to be noticed by observant eyes. The age of metal was about to dawn, though no one yet suspected that certain stones held secrets that would reshape the human world entirely. The first people to hold metal in their hands likely had no concept of what they had discovered. Imagine, if you will, a warm afternoon somewhere in the highlands of the ancient Near East, perhaps 9 or 10,000 years ago. A person walking along a rocky outcrop notices something unusual catching the sunlight. Among the ordinary grey and brown stones lies something different. A small, heavy nugget with a reddish golden gleam, unlike anything in their experience with ordinary rocks. This moment, repeated countless times across different landscapes and different millennia, marked humanity's first acquaintance with metal. But these weren't the metals that required fire and furnaces to extract. These were native metals, pure elements that existed in nature in their finished metallic state, waiting to be found like treasures scattered across the Earth's surface. Gold was perhaps the most captivating of these discoveries. Heavy, soft, and radiantly yellow, gold appeared in streams and rivers as nuggets and flakes, weathered free from the rocks that had held them. Its resistance to tarnishing meant that even ancient pieces retained their luster, making them impossible to ignore. Silver, too, existed in native form, though less commonly, with its cool white gleam and similar malleability. But it was copper, more widespread than gold or silver, that would prove most significant to humanity's metalworking future. Native copper occurs in several regions around the world, most notably around the Great Lakes of North America, in the mountains of the Near East, and in isolated deposits across Europe and Asia. Unlike the copper that would later be smelted from green and blue ores, these native deposits were pure metal, sometimes forming in strange dendritic shapes like frozen lightning, or in solid nuggets embedded in rock matrices. Early peoples recognized these finds as special. The weight, the color, the way they felt different from stone, all marked these materials as worthy of attention. The earliest experiments with these native metals were remarkably simple yet profoundly important. Someone, somewhere, discovered that these unusual materials could be shaped. Unlike stone, which had to be flaked or ground into form, native metals responded to hammering. Strike a piece of native copper with a stone, and instead of shattering, it would flatten and spread. Continue hammering, and you could shape it, elongate it, even form it into simple tools or ornaments. Archaeological evidence places these first hammered metal objects remarkably early in human history. Sites in Anatolia, the region of modern-day Turkey, have yielded small copper beads and pins dating to around 8700 BCE, crafted from native copper through nothing more than patient cold working. These weren't smelted, weren't heated into molten form. They were simply found, hammered, and shaped. The process, which we now call cold working or cold hammering, had its limitations. Native copper, while initially soft and workable, becomes harder and more brittle as it's hammered. The metal's internal structure changes with each blow, and eventually it can crack or fracture if worked too aggressively. But early metalworkers, through patient experimentation, discovered they could only push the material so far before it needed to rest or before their work risked failure. In the Great Lakes region of North America, indigenous peoples developed a sophisticated tradition of working native copper that stretched back thousands of years. The copper deposits there were among the richest in the world, sometimes appearing as massive chunks of pure metal weighing thousands of pounds. Without access to smelting technology, these craftspeople became masters of cold working, creating spear points, knives, fish hooks, bracelets, and ceremonial objects through hammering, grinding, and polishing. Some of these objects traveled vast distances through trade networks, finding their way to sites hundreds of miles from the copper sources. The appeal of these early metal objects wasn't primarily functional, at least not at first. A hammered copper awl or pin certainly had its uses, but stone tools of the era were, in many ways, more effective for most tasks. Instead, the value of these first metal objects lay in their novelty, their beauty, and their rarity. They were exotic, special, worthy of prestige. Gold and silver, too soft for most practical applications, became prized for ornaments, their imperishable shine connecting them with the eternal. Yet within these simple acts of hammering and shaping, our ancestors were learning fundamental lessons about metals that would echo through all subsequent metallurgical development. They were discovering that these materials had properties unlike anything else they knew. Metals could be shaped without breaking, could hold an edge differently than stone, could be polished to an unprecedented shine, and possessed a satisfying weight and density. Different cultures encountered native metals at different times and developed different relationships with them. In the Middle East, where copper, gold, and silver all appeared in native form in various locations, metalworking with found metals developed alongside advanced stone tool industries. In Europe, native gold and copper drew attention, but remained rare enough that their use was limited to special objects. In Southeast Asia and parts of Africa, similar independent discoveries occurred as people encountered these unusual materials in their landscapes. The timeline of these discoveries stretches across millennia, from the first hammered beads in the 9th millennium BCE to continuing traditions of native metalworking that persisted into historical times. What's remarkable is not the speed of development, but the patience and attention that early peoples brought to these materials. Each generation of workers learned a little more, remembered a little more, and passed along their knowledge to those who followed. As centuries passed, communities began to recognize certain locations as sources of these valuable materials. Native copper deposits became known places, visited and revisited. River gravels that yielded gold became valued territories. The metal objects themselves became markers of connection between distant places, as trade networks carried these precious items far from their sources. A copper bead found in a burial site might have traveled for weeks or months before reaching its final resting place. each exchange along the way recognizing its worth. The stage was being set, gradually and quietly, for a much more dramatic transformation. These early metalworkers, hammering their native copper and admiring their golden ornaments, couldn't have known that some of the rocks in their environment held metals in disguised forms. They couldn't have imagined that certain stones, when subjected to fire, would release copper or tin or lead. But their familiarity with how metals looked, felt, and behaved meant that when accidents or experiments eventually revealed these secrets, they would recognize what they had found. The age of native metals was, in many ways, a gentle introduction to a relationship that would transform human civilization, a first handshake with the elemental forces that lay waiting in the earth. The discovery that would change everything began, most likely, with fire and accident. Somewhere in the ancient Near East, perhaps in the highlands of Anatolia or the Zagros Mountains, someone noticed something extraordinary happening in the embers of their campfire. The transformation would have seemed almost magical at first, a mystery that demanded explanation and experimentation. Imagine a cooking fire built atop rocks that happened to contain copper minerals. As the flames burned hot through the night, these particular stones, rich in malachite or azurite with their distinctive green and blue colors, began to behave differently than ordinary rocks. Within the intense heat, tiny beads of reddish metal began to appear, separating themselves from the stone matrix that had held them prisoner since the Earth's formation. This copper, unlike the native nuggets people had been hammering for thousands of years, was being born from stone itself. The earliest evidence we have for this revolutionary process dates to around 5000 BCE, though the discovery may have occurred somewhat earlier. Sites in modern-day Iran and Iraq have yielded copper artifacts that show unmistakable signs of having been smelted rather than simply hammered from native metal. The distinction is crucial. While native copper could be found and worked, it was relatively rare. But copper-bearing minerals were far more abundant, occurring in colorful veins and deposits across many landscapes. If one could learn to extract the metal from these stones, an almost limitless supply became available. The process that ancient experimenters gradually developed was elegant in its simplicity, yet required careful observation and control. Copper ore, once recognized for what it was, needed to be heated in the presence of charcoal or another fuel source. The fire had to reach temperatures of around 1000 degrees Celsius, far hotter than an ordinary cooking fire, but achievable with the right techniques. As the ore heated in this reducing atmosphere, where carbon from the fuel consumed the oxygen, the copper oxide in the mineral gave up its oxygen and transformed into pure metallic copper. We can picture these early metallurgists tending their fires with careful attention, adding fuel and ore in measured amounts, protecting the operation from wind that might cool the flames or introduce too much oxygen. They would have learned through countless trials that certain colored stones yielded copper while others did not. The brilliant green of malachite and the deep blue of azurite became treasured indicators of copper-bearing rock. They discovered that crushing the ore into smaller pieces helped the process along, and that maintaining the fire at high temperature for extended periods produced better results. The copper that pooled at the bottom of these early smelting operations would have been a revelation. Unlike the small nuggets of native copper that ancient peoples had collected, here was metal that could be produced in quantity, limited only by the availability of ore and fuel. The molten copper could be poured into impressions in sand or stone, creating shapes that would have been impossible to achieve through hammering alone. When cooled, this smelted copper possessed the same wonderful properties as native copper. It was malleable, it could be shaped and reshaped, and it took a fine edge. Knowledge of this transformative technique spread gradually across the ancient Near East during the 6th and 5th millennia BCE. Archaeological evidence traces the expansion of copper smelting from its earliest centers into surrounding regions. Settlements that had access to copper ore deposits gained a significant advantage, and the distinctive green and blue stones became objects of trade and desire. Communities began to organize themselves around this new capability, with some individuals specializing in the demanding work of fire tending and metal extraction. The landscape itself began to change in subtle ways around these early smelting centers. The constant demand for charcoal meant that forests near copper-working communities faced increasing pressure. Trees were cut, converted to charcoal through slow, controlled burning, and then consumed in the hungry fires of the smelting operations. The slag, the rocky waste material that separated from the copper during smelting, began to accumulate in heaps near workshops, creating artificial hills that archaeologists would discover millennia later. In different regions, metallurgists developed variations on the basic smelting technique, adapted to their local materials and conditions. Some built small clay furnaces that concentrated heat more effectively than open fires. Others dug pits that they lined with clay, creating crucibles in the earth itself. The invention of the bellows, or simple blowpipes made from reeds or hollow bones, allowed workers to force air into the fire, raising temperatures even higher and making the smelting process more efficient and reliable. The social implications of this new technology rippled outward through ancient societies. Those who possessed the knowledge of smelting held valuable expertise, a kind of secret knowledge that commanded respect and resources. Copper objects began to appear more frequently in graves and settlements, no longer quite as rare as they had been when only native metal was available. Yet smelted copper still required effort, skill, and resources to produce, so it remained precious, a material associated with status and importance. As the centuries passed and the 5th millennium BCE gave way to the 4th, copper smelting became increasingly sophisticated. Metallurgists learned to judge the quality of ore by its appearance and weight, to maintain their furnaces at optimal temperatures, and to pour the molten metal into increasingly complex molds. The ability to create not just simple shapes, but tools with functional designs, weapons with carefully planned forms, and ornaments with intricate details transformed what was possible. This period represents humanity's first steps into true extractive metallurgy, the art and science of winning metal from stone. It was a threshold moment in our species' relationship with the material world. No longer were people limited to shaping what they found in nature. Now, they could transform one substance into another through the application of fire and technique, turning dull rock into gleaming metal. The implications of this power would unfold over the coming millennia. But even in these early days, something fundamental had shifted. The copper revolution had begun, quietly at first in scattered workshops and settlements, but with a momentum that would prove unstoppable. The knowledge, once discovered, could not be forgotten. It would spread, evolve, and combine with other discoveries yet to come, setting humanity on a path toward ever greater mastery of the metals sleeping in the earth. The knowledge of copper smelting, once discovered, began to flow outward from its earliest centers, like water seeking new ground. As this transformative skill spread across ancient communities, the lives of countless people began to change in ways both subtle and profound. The Copper Age had truly begun, and with it came an entirely new relationship between human beings and the materials of the earth. Imagine, if you will, a village nestled in the foothills of an ancient landscape where smoke rises gently from a workshop at the settlement's edge. Inside, a craftsperson tends a small furnace, carefully controlling the flow of air through primitive bellows made from animal skin. The glow of molten copper cast dancing shadows on clay walls, and the rhythmic sound of hammering creates a steady, almost meditative rhythm that marks the passage of working hours. This scene, repeated in countless variations across the ancient world, represents humanity's first sustained engagement with metalworking as a regular, purposeful craft. The objects that emerged from these early workshops were remarkably diverse. Copper was soft enough to work, yet hard enough to serve practical purposes that stone could not match. Awls for piercing leather became prized possessions, their sharp points maintaining their shape far longer than bone equivalents. Fishhooks of copper curved into forms that were difficult to achieve with other materials, opening new possibilities for communities living near water. Pins and needles allowed for more refined textile work, enabling the creation of more complex garments and decorative items. Axes and adzes of copper, while not as sharp-edged as the finest flint, offered distinct advantages. Unlike stone, which could shatter unexpectedly along hidden fractures, copper was predictable. When a copper blade dulled, it could be resharpened. When it bent, it could be straightened. This reliability, this capacity for repair and renewal, represented a fundamental shift in how humans could relate to their tools. The ornamental applications of copper were equally important to these ancient societies. The warm, reddish glow of polished copper held an aesthetic appeal that transcended mere function. Bracelets, rings, and beads of copper became markers of status and wealth. Thin sheets of copper were hammered into decorative discs that caught the light, creating adornments that would have seemed almost magical to communities previously limited to shells, stones, and bones for decoration. As craftspeople worked with copper over generations, they made discoveries that would prove crucial to the advancement of metallurgy. One of the most important was the phenomenon known as work hardening. When copper is hammered repeatedly, its crystalline structure becomes compressed and tangled, causing the metal to become harder and more brittle. A copper blade that began soft could be made significantly harder through patient, systematic hammering. This process allowed ancient metallurgists to enhance the properties of their creations, tailoring the metal's characteristics to specific purposes. Yet work hardening presented a challenge. push the process too far, and the copper would become so brittle that it might crack or shatter under stress. The solution to this problem was discovered through patient observation and experimentation. When work-hardened copper was heated to a certain temperature and allowed to cool slowly, its crystalline structure reorganized itself, and the metal became soft and workable once more. This process, known as annealing, was a revelation. It meant that a craftsperson could alternate between hammering to shape and strengthen the metal, and heating to restore workability, achieving forms and properties that neither process alone could produce. The cycle of hammering and annealing became a kind of dance between the metalworker and the material. A copper blade might be shaped roughly through hammering, then annealed to relieve the internal stresses, then hammered again to refine the shape and harden the edge, then annealed once more, and so on through multiple iterations until the desired form and hardness were achieved. This intimate knowledge of the metal's behavior, passed from master to apprentice through demonstration and practice, represented a sophisticated understanding of material properties that arose not from theory, but from countless hours of careful, observant work. The workshops where this knowledge was practiced became special places within their communities. The ability to transform dull, unremarkable stones into gleaming, useful metal required not only skill but also resources. Fuel for the furnaces, whether wood or charcoal, had to be gathered and stored. Clay for molds and crucibles needed to be prepared with the right consistency. The copper ore itself had to be transported from wherever it was found, sometimes over considerable distances. A successful metalworking operation thus required planning, resource management, and often the support of the broader community. In some settlements, metalworking became a specialized occupation. Certain individuals dedicated themselves to mastering the techniques, developing the sensitivity of hand and eye needed to judge temperatures by color, to hear in the ring of hammered metal whether it needed annealing, to recognize the subtle signs that indicated proper smelting conditions. These specialists might trade their products for food, textiles, and other necessities, creating some of the earliest forms of craft specialization in human societies. The spread of copper tools had ripple effects that touched many aspects of daily life. Wooden structures could be joined more precisely with copper tools than with stone. The cultivation of harder soils became more feasible with copper implements. Even the preparation of food benefited from copper knives that held their edges and could be cleaned more easily than stone blades. Yet for all its advantages, copper had limitations that would become increasingly apparent over time. It was relatively soft, even when work hardened to its maximum extent. Tools required frequent resharpening. Weapons of copper, while functional, could not match the hardness of stone. The metal's very malleability, which made it workable, also meant it was prone to bending and deforming under heavy use. Still, the Copper Age represented a crucial stepping stone, a period during which human beings learned the fundamental principles of working with metals. The skills developed during this era, the understanding of heating and hammering, of controlling fire and recognizing the properties of different materials, would prove essential when the next great metallurgical advancement emerged. The patient craftspeople of the Copper Age, tending their furnaces and perfecting their techniques, were laying groundwork for innovations they could scarcely imagine, preparing the way for an alloy that would define a new epoch in human history. The craftspeople of the ancient world had by now grown comfortable with copper, understanding its moods and temperament, as well as any farmer knew the seasons. They had learned to heat it, hammer it, and coax it into shapes both useful and beautiful. Yet in the persistent way of human curiosity, they continued to experiment, to wonder, to try new combinations of the materials the earth offered them. Somewhere in the ancient Near East, perhaps in Mesopotamia or Anatolia, around 3500 BCE, though we cannot know the exact place or moment, something remarkable happened. A metallurgist, working with copper ore, produced a metal that behaved differently from anything seen before. This new material flowed more easily when molten, making it simpler to cast into complex shapes. When it cooled and solidified, it proved harder than pure copper, holding a sharper edge and resisting wear with greater stubbornness. Bronze had entered the world. The discovery may well have been entirely accidental. In those ancient times, metallurgists worked with whatever ores they could find in their local landscapes, and the composition of these ores varied considerably from one location to another. Some copper ores naturally contained other metals mixed within them, invisible to the eye, but present nonetheless in the stone's crystalline structure. Tin was one such companion metal, and when an ancient smelter happened to heat copper ore that contained tin, or perhaps mix different types of ore together, the resulting metal would have displayed these curious new properties. Imagine the moment of realization when a craftsperson first noticed that this particular batch of copper seemed different, superior. Perhaps they were casting a tool and found the metal filled the mold more completely, capturing every detail. Perhaps they were sharpening a blade and discovered it maintained its edge through work that would have blunted pure copper. However the recognition came, it sparked a question that metallurgists then had to answer. How could this superior metal be created deliberately, time and time again? The answer lay in identifying what made this metal different. Through experimentation and careful observation, ancient metallurgists gradually recognized that certain ores, or combinations of ores, produced this better metal. The key ingredient was tin, though understanding this relationship took time and countless trials. Eventually, they learned that mixing roughly 1 part tin with 9 parts copper created the optimal alloy, a proportion that balanced strength, workability, and durability. Tin itself presented its own mysteries. The metal could be smelted from ores like cassiterite, a mineral that often appeared as dark, heavy crystals in stream beds, where water had worn it from underground deposits and concentrated it in gravels. In its pure form, tin was soft and silvery, hardly impressive on its own. It seemed almost magical that adding this unassuming metal to copper could transform the copper's very nature. The metallurgical transformation that occurred when copper and tin united was invisible to ancient eyes, but profound in its effects. The tin atoms, smaller than copper atoms, nestled into the spaces within copper's crystalline structure, disrupting the orderly arrangement of copper atoms. This disruption made it harder for the metal to deform under pressure, increasing its strength and hardness. The combination also lowered the melting point compared to pure copper, allowing the molten bronze to flow more readily into molds and making the casting process more reliable and predictable. For the craftspeople who worked with bronze, these properties open new possibilities. Tools could be made sharper and would stay sharp longer through extended use. Weapons became more effective and durable. Decorative objects could be cast with finer detail, as the more fluid bronze captured the subtle textures of the molds more faithfully. The metal's golden color, slightly different from copper's reddish hue, gave finished objects a distinctive and pleasing appearance that societies valued for both functional and ornamental purposes. The advantages of bronze were clear enough that knowledge of its creation spread, though perhaps not as quickly as we might imagine. Metallurgy in these ancient times was specialized knowledge, closely held by those who practiced it. The techniques were learned through apprenticeship and demonstration, passed from master to student in workshops, where the secrets of the craft were guarded. Still, bronze was too valuable an innovation to remain confined to one region, and gradually, through trade, migration, and the inevitable sharing that occurs when cultures meet, the knowledge rippled outward. Different regions developed their own preferences for bronze composition, adjusting the ratio of tin to copper based on the intended use of the final product. Bells, for instance, benefited from a higher tin content that made the bronze harder and gave it a clear, ringing tone when struck. Tools and weapons typically used the standard proportion, balancing hardness with the ability to be sharpened and repaired. Mirrors and decorative items might use yet different proportions, chosen for their color and reflective properties. The birth of bronze did not mean the immediate abandonment of pure copper. Rather, the two metals coexisted, each finding its appropriate uses. Copper remained valuable for items where its particular properties suited the purpose, while bronze gradually claimed dominance for applications where superior hardness and durability mattered most. This transition unfolded over generations as metalworkers refined their understanding and as bronze-making knowledge became more widespread. As word of this superior metal spread across ancient trade routes, as merchants carried bronze objects to distant markets where they impressed local rulers and craftspeople, a new demand arose. Societies that had relied on copper now wanted bronze, and this desire would reshape the ancient world in ways both subtle and dramatic. For bronze required not just one metal, but two. And while copper ores were relatively common, tin proved far more elusive, found in only certain regions scattered across the known world. This scarcity of tin would soon drive the creation of trade networks spanning vast distances, connecting communities that had never before had reason to interact. The search for tin would send prospectors into remote mountains and distant lands, would fill merchant ships with precious cargo, and would create dependencies between regions separated by weeks or months of difficult travel. The Bronze Age had truly begun, and with it came a new, interconnected world, bound together by the need for metals that, when combined, created something greater than either could be alone. The discovery of bronze had created something unprecedented in human experience, a demand that could not be satisfied locally. A bronze maker needed two different metals, and while copper could be found in many regions across the ancient world, tin was remarkably scarce. This simple geological fact would reshape human civilization, drawing invisible lines across continents and seas, connecting distant peoples who had never seen one another's faces. Imagine standing in a workshop in ancient Mesopotamia, around 3,000 years before the Common Era. The master craftsman examines his dwindling supply of tin, a silvery metal that arrived weeks ago from somewhere far beyond the horizon. He knows only that it comes from the north, carried by traders who speak unfamiliar languages and tell stories of mountains and rivers he cannot quite picture in his mind. Without this mysterious material, he cannot make bronze. Without bronze, his patrons cannot obtain the tools and weapons they require. The whole economy of his city depends on a supply chain stretching farther than most people will ever travel in their lifetimes. The tin routes became the arteries of the Bronze Age world, from the mountains of Afghanistan, where deposits of cassiterite, the primary tin ore, could be found in certain valleys. Caravans wound their way westward toward Mesopotamia and the cities of the Fertile Crescent. These journeys might take months, passing through varied territories, across rivers and mountain passes, through lands controlled by different peoples who each took their share of the profits. The tin ingots traveled in standardized shapes that archaeologists still uncover today, their forms revealing an ancient understanding of trade and quality control. In the opposite direction, other routes stretch toward the tin sources of what we now call Cornwall and Devon, at the southwestern tip of Britain. Here, in streams and shallow deposits, tin could be extracted from the earth through placer mining and simple smelting techniques. The Phoenician traders, those master sailors of the ancient Mediterranean, ventured far into the Atlantic waters to reach these distant sources. They established trading posts along the coasts, creating relationships with local peoples who controlled access to the precious ore. These same routes would later carry tin from the Iberian Peninsula and from mysterious locations that ancient writers mentioned, but whose precise locations remain debated by scholars today. The waterways of the Mediterranean became highways of exchange. Ships laden with copper from Cyprus, an island whose very name may derive from the metal, sailed toward ports where tin arrived from distant lands. The island of Crete, positioned strategically in the middle of these sea routes, flourished as a center of Bronze Age civilization, its palaces decorated with frescoes showing elegant figures, and its workshops producing sophisticated bronze objects. The Minoan traders understood that their geographic position was their fortune, and they facilitated exchanges between Egypt, the Near East, and the lands to the north and west. Trade in bronze-making materials was never simple commerce in raw materials alone. Along with the tin and copper, traveled ideas, techniques, and artistic styles. A merchant from Babylon might observe metalworking methods in Anatolia and carry that knowledge home. A craftsman might travel with a shipment of copper ingots, offering his services in a distant port and learning new approaches from the local metalworkers there. Religious beliefs, decorative motifs, and technological innovations flowed along the same paths as the metals themselves. The archaeological evidence reveals the scale of this exchange. Shipwrecks discovered on the Mediterranean seafloor have yielded remarkable cargo. Hundreds of copper ingots shaped like stretched ox hides, each weighing as much as a grown man could comfortably carry. Tin ingots travel alongside them, along with pottery, glass, and precious materials from multiple regions. These ships were floating warehouses, their holds representing connections between a dozen different cultures and economies. When one of these vessels sank in a storm, it carried to the bottom a snapshot of Bronze Age globalization. Overland routes were equally vital, though they left fewer dramatic traces for modern archaeologists to discover. Through the mountain passes of Central Asia, across the steppes where nomadic peoples moved with the seasons, tin and copper traveled in both directions. The cultures of the Eurasian interior, often overlooked in favor of the great literate civilizations, played essential roles as intermediaries and transporters. They developed their own distinctive bronze-working traditions, influenced by contact with both Eastern and Western techniques. The quest for metals drove exploration and geographic knowledge. Ancient peoples mapped their world in terms of resource locations, and the boundaries of the known world expanded as merchants ventured farther in search of reliable supplies. The legendary expeditions of antiquity often had practical metal-seeking origins beneath their mythological embellishments. When ancient texts speak of heroes voyaging to distant lands and returning with treasures, we might hear echoes of very real journeys undertaken to establish new sources of tin or copper. This dependence on long-distance trade created vulnerabilities as well as opportunities. A disruption in the supply lines, whether from political conflict, natural disaster, or the collapse of an intermediary kingdom, could have cascading effects across the interconnected Bronze Age world. Metalworkers might find themselves unable to obtain tin, forcing them to experiment with alternative alloys or to recycle old bronze objects. Kingdoms that controlled important routes or deposits could exercise influence far beyond what their military power alone might suggest. The trade networks also encouraged the development of related technologies and practices. Standardized weights and measures emerged to facilitate fair exchange across cultural boundaries. Methods of assessing metal purity became more sophisticated, as both buyers and sellers needed confidence in the quality of materials changing hands. Record-keeping systems evolved to track complex transactions involving multiple parties, perhaps contributing to the development and spread of early writing systems. In some regions, the scarcity of tin led metalworkers to develop alternative approaches. Arsenical bronze, made by alloying copper with arsenic rather than tin, served as a substitute in areas where tin was particularly difficult to obtain. Though the fumes from working with arsenic posed dangers to the craftspeople, this alternative allowed bronze making to flourish in locations far from tin sources. Each region adapted its metallurgical practices to the materials available, creating a diverse landscape of techniques and traditions across the Bronze Age world. As centuries passed, the trade routes became more established, the relationships more routine, and the flow of materials more reliable. Entire civilizations structured their economies around the acquisition and distribution of bronze-making materials. The stage was set for these same civilizations to rise to unprecedented heights of complexity and achievement, built upon foundations of trade networks that span the known world. The flow of tin and copper across their ancient trade routes had created something unprecedented in human history, a web of connections linking distant peoples in a shared technological enterprise. Now, as bronze spread more widely and became more readily available, entire civilizations began to reshape themselves around this remarkable material. The true transformative power of bronze was about to reveal itself not merely in individual tools or weapons, but in the fundamental reorganization of human society. Along the banks of the Tigris and Euphrates rivers, the Mesopotamian cities gleamed under the desert sun. Here, in the land between two rivers, bronze had become the foundation of an increasingly complex civilization. The temples rose higher than ever before, their construction made possible by bronze tools that could cut through timber and shape stone with unprecedented precision. Bronze chisels allowed artisans to carve intricate inscriptions into stone monuments, preserving laws and stories for future generations. The famous Code of Hammurabi, carved into black diorite around 1750 BCE, was made possible by bronze tools capable of working such hard stone with fine detail. In the agricultural fields surrounding these cities, bronze sickles harvested grain more efficiently than their flint predecessors ever could. The bronze blade held its edge longer and could be resharpened more easily. Farmers could clear land more quickly with bronze axes, bringing new fields into cultivation. Bronze-tipped plows bit more deeply into the earth, turning soil that had resisted earlier implements. This agricultural revolution meant surplus food, and surplus food meant that more people could specialize in other pursuits. Craftspeople, priests, administrators, and soldiers could dedicate themselves entirely to their vocations, supported by the abundance that bronze-enhanced agriculture provided. The administrative machinery of these river valley civilizations grew more sophisticated with bronze. Scribes used bronze styluses to press cuneiform characters into clay tablets, recording transactions, inventories, and correspondence. The very act of governance became more complex and far-reaching, because bronze tools made it possible to maintain detailed records on a scale previously unimaginable. Kings could track taxation, manage stored grain, and coordinate large construction projects with unprecedented precision. Far to the west, along the Nile River, Egyptian civilization flourished with bronze as its technological backbone. The Great Pyramids of the Old Kingdom had been built primarily with copper tools, but as bronze became more available during the Middle Kingdom and New Kingdom periods, Egyptian craftspeople accomplished even more remarkable feats. Bronze saws cut through limestone and granite. Bronze drills hollowed out stone vessels and carved detailed hieroglyphics. The magnificent temples at Karnak and Luxor, with their towering columns and intricate reliefs, were shaped in part by bronze implements held in skilled hands. Egyptian bronze workers created objects of stunning beauty and utility. Bronze mirrors, polished to a high shine, allowed the wealthy to admire their reflections. Bronze vessels held precious oils and cosmetics. Bronze fittings adorned furniture and chariots. The pharaohs themselves were buried with bronze implements they might need in the afterlife, including tools, weapons, and ceremonial objects that showcased the highest achievements of metallurgical art. The military applications of bronze transformed warfare and consequently the political landscape of the ancient world. Bronze armor protected soldiers as never before. Breastplates, helmets, and greaves meant that warriors could engage in closer combat with greater confidence. Bronze-tipped spears and arrows flew straighter and struck harder than earlier weapons. The bronze sword, combining a sharp edge with structural strength, became the symbol of military power across the ancient world. These military advantages meant that civilizations with reliable access to bronze held tremendous power over their neighbors. The chariot warriors of the Bronze Age, equipped with bronze weapons and armor, thundered across battlefields from Egypt to Mesopotamia to the steppes of Central Asia. These chariots themselves were marvels of Bronze Age engineering, held together with bronze fittings and carrying warriors armed with bronze-tipped arrows and spears. In the Indus Valley, along the rivers that flow from the Himalayas to the Arabian Sea, another great civilization employed bronze in its own distinctive ways. The cities of Harappa and Mohenjo-daro, with their remarkably advanced urban planning, used bronze tools to create sophisticated drainage systems, multi-story buildings, and standardized fired bricks. Bronze weights and measures facilitated trade across long distances, creating economic networks that reached from the Persian Gulf to the mountains of Afghanistan. The bronze workers of the Indus Valley civilization created objects of remarkable refinement. The famous dancing girl statue from Mohenjo-daro, cast in bronze using the lost wax method, demonstrates both technical mastery and artistic sophistication. These craftspeople understood how to create detailed figurines, practical tools, and ornamental objects that speak across millennia of a culture that valued both utility and beauty. Far to the east, in the Yellow River Valley of ancient China, bronze technology arrived and flourished in ways uniquely suited to Chinese civilization. The Shang dynasty, beginning around 1600 BCE, became renowned for bronze vessels of extraordinary complexity and artistry. These were not simple containers, but elaborate ritual objects covered with intricate decorations. The bronze workers of ancient China mastered piece mold casting techniques that allowed them to create vessels with complex surface decorations that would have been nearly impossible to achieve through other methods. These Chinese ritual bronzes served crucial functions in ancestor worship and state ceremonies. The ability to cast large, elaborate bronze vessels became a mark of political legitimacy and spiritual authority. The bronze itself was seen as a precious material suitable for communicating with ancestors and spirits. The inscriptions cast into these vessels recorded important events, creating historical records preserved in the metal itself. Across these varied civilizations, bronze enabled a new scale of monumental construction. Bronze tools meant that stone blocks could be shaped more precisely, timbers cut more efficiently, and construction projects coordinated on a grander scale. The palaces of Minoan Crete, the fortifications of Mycenaean Greece, the temples of the Hittite Empire, all rose in part because bronze tools made their construction feasible. The wealth generated by bronze technology also enabled the arts to flourish. Sculptors used bronze tools to carve stone statues and reliefs. Musicians played instruments with bronze strings or bronze components. The leisure time created by agricultural surplus, itself dependent on bronze tools, allowed literature, philosophy, and mathematics to develop in ways that would have been impossible when every person's labor was needed merely for survival. As the centuries passed and bronze became more common, its impact deepened and spread. Technologies that had once been secrets guarded by specialized craftspeople gradually became more widely known. Regional variations emerged as different cultures adapted bronze working techniques to their own needs and aesthetic preferences. Yet everywhere bronze touched, it left the same fundamental legacy. Societies became more complex, more productive, and more capable of coordinating large-scale human efforts toward common goals. The story of bronze and civilization is ultimately a story of how material capabilities shape human possibilities. With bronze, ancient peoples could feed more mouths, protect larger territories, record more information, and create lasting monuments. The metal flowing through ancient trade routes carried more than just copper and tin. It carried the potential for human societies to grow beyond anything their ancestors could have imagined, creating the foundations upon which all subsequent civilizations would build. The great civilizations built upon bronze required not just raw materials, but skilled hands and accumulated knowledge to transform those materials into useful objects. Behind every bronze sword, every ceremonial vessel, every agricultural implement, stood workshops where master craftspeople practiced their ancient art. These spaces, often located near temples or palaces, hummed with focused activity and the transmission of secrets passed from one generation to the next. Step inside one of these workshops, and your senses would be immediately engaged. The air carried the distinctive smell of hot metal and charcoal smoke. The steady rhythm of hammers striking metal created a kind of industrial music, punctuated by the hiss of hot bronze meeting water. Light filtered through doorways and windows, illuminating particles of dust and smoke that danced in the beams. Along the walls, tools hung in careful arrangement, each one placed exactly where the craftsperson expected to find it. The bronze worker's craft began with careful preparation. Copper and tin had to be obtained in the correct proportions, typically about 9 parts copper to 1 part tin, though the exact ratio varied according to the intended purpose of the finished object. Tools and weapons required slightly different mixtures than decorative items or vessels. This knowledge of proportions represented generations of experimentation, and master craftspeople guarded their particular formulations closely. The smelting process itself demanded constant attention. Furnaces constructed of clay and stone had to reach temperatures around 1,000 degrees to melt bronze effectively. Maintaining these temperatures required careful management of fuel and airflow. Bellows, often made from animal skin stretched over wooden frames, pumped air into the furnace. In larger workshops, apprentices took turns operating the bellows in steady rhythm, their arms working tirelessly to keep the fire hot enough. Once the bronze reached its molten state, glowing with an orange light that seemed almost alive, the real artistry began. For simpler objects, open molds carved from stone or formed from clay provided the shape. The metallurgist would carefully pour the liquid metal into these molds, watching as the glowing bronze flowed into every crevice and detail. The pouring itself required a steady hand and precise judgment, as hesitation or spillage could ruin hours of preparation. But the most sophisticated bronze objects demanded more elaborate techniques. The lost wax casting method, developed independently in different regions of the ancient world, allowed craftspeople to create objects of remarkable complexity and beauty. This process began not with metal but with beeswax, which the artisan carefully sculpted into the exact form of the desired final object. Every detail, every decoration, every subtle curve had to be perfected in this wax model. Around this wax form, the craftsperson built up layers of fine clay, creating a sturdy mold. Once the clay hardened, the entire assembly was heated, The wax melted and drained away, leaving behind a perfect negative space within the clay mold. Into this space, molten bronze would flow, taking the exact form of the original wax model. After cooling, the clay mold was carefully broken away, revealing a bronze object that preserved even the finest details the artisan had carved in wax. This technique meant that each lost wax casting was unique. Unlike simple open molds that could be reused, the clay mold for lost wax casting was destroyed in the process. Every ceremonial vessel, every decorated weapon, every intricate piece of jewelry represented not just skill, but also a singular creative act that could never be perfectly replicated. Different cultures developed their own variations and specializations in bronze working. In ancient China, craftspeople created massive bronze vessels called ding, used in ritual ceremonies. These vessels featured intricate geometric patterns and sometimes elaborate handles formed as animal figures. The precision required to cast such large objects without flaws demonstrated extraordinary technical mastery. Chinese bronze workers developed piece mold casting techniques that allowed them to create complex surface decorations by assembling multiple sections of carved mold. In the Mediterranean world, Greek and Etruscan workshops became famous for bronze statuary. Life-sized and even larger figures required careful planning, as casting such large objects in one piece presented enormous challenges. Many statues were instead cast in sections that were later joined together, the seams carefully worked and polished until they became invisible. The knowledge of how different thicknesses of bronze would cool and contract guided the placement of these joints. The workshop represented more than just a place of production. It functioned as a school where knowledge passed from master to apprentice through years of observation and practice. Young apprentices might spend their first months simply maintaining the fire, learning to judge temperature by the color of the flames and the behavior of the coals. Gradually, they would progress to preparing molds, mixing alloys, and eventually handling the molten metal themselves. This transmission of knowledge remained largely oral and practical. While some cultures recorded basic recipes and techniques, the subtle judgments that separated adequate work from exceptional work lived in the hands and eyes of experienced craftspeople. How to recognize when bronze reached the ideal pouring temperature, how much to thin the walls of a vessel for the right combination of lightness and strength, how to repair a casting flaw without weakening the finished piece. These skills came only with time and practice. The status of bronze workers varied across different societies. In some cultures, they held positions of honor, their workshops supported by temples or royal courts. Their ability to transform earth into gleaming metal seemed almost magical, earning them respect and sometimes suspicion. In other societies, while their products were highly valued, the workers themselves occupied more modest social positions, recognized as skilled laborers rather than artists. Yet regardless of their social standing, these craftspeople understood that they worked with materials that held power. Bronze weapons decided battles. Bronze tools cleared forests and tilled fields. Bronze vessels held offerings to gods and ancestors. Every object that left the workshop carried with it the accumulated knowledge of centuries and the focused skill of human hands working with fire and metal. As evening fell and workshops began to quiet, the last fires would be carefully banked. coals covered to preserve them for the next day's work. Tools were cleaned and stored, molds inspected for cracks or damage, and the day's production examined one final time. Tomorrow would bring new challenges, new objects to create, and the ongoing refinement of techniques that had already served civilization for thousands of years. As the bronze workers perfected their ancient craft, hammering and casting their familiar alloys in workshops across the known world, there existed another metal that had captured human imagination for millennia. This metal fell from the sky in streaks of fire, arriving to Earth wrapped in stone and mystery. Iron had been known to humanity far longer than most people might imagine, yet it remained scarce, precious, and extraordinarily difficult to work with purpose. The first iron that humans ever touched came not from the ground beneath their feet, but from the heavens above. Meteorites, those wandering fragments of celestial bodies that occasionally survive their fiery descent through our atmosphere, brought pure iron to ancient peoples in small, irregular chunks. These sky stones were recognized as special from their very first discovery. Heavier than ordinary rock, they possessed an unusual luster when their surfaces were cleaned, and they behaved entirely differently from any earthly stone when struck or heated. Ancient Egyptians called meteoritic iron metal from the sky, and they valued it more highly than gold. Beads of meteoritic iron have been found in Egyptian graves dating back to 3200 BCE, carefully shaped and strung alongside precious stones. The young pharaoh Tutankhamun, whose tomb has given us such extraordinary glimpses into ancient Egyptian life, was buried with a dagger whose blade was crafted from meteoritic iron. Chemical analysis of this blade has confirmed its celestial origin, showing concentrations of nickel that are characteristic of iron meteorites, but not of earthly iron ores. The rarity of meteoritic iron meant that only the most important people possessed objects made from it. These pieces were not merely valuable because of their scarcity, but because they represented something fallen from the realm of the gods. In many ancient cultures, meteorites were themselves objects of worship, tangible evidence of divine power, made manifest in the physical world. To craft a tool or weapon from such material was to work with the substance of the heavens themselves. But meteoritic iron presented a profound puzzle to the bronze workers, who occasionally received small amounts of it. The techniques that worked so beautifully with copper and bronze failed entirely with iron. Bronze could be melted at temperatures achievable in ordinary furnaces, around 1100 degrees Celsius. The molten bronze could then be poured into molds, cooled, and finished. Iron, however, refused to cooperate with this familiar process. Pure iron requires temperatures of over 1500 degrees Celsius to melt, far beyond what ancient furnaces could achieve. When bronze workers heated iron in their furnaces, expecting it to liquefy as copper did, the iron simply sat there, glowing red hot, then yellow hot, then white hot, but never flowing, never melting into that useful liquid state. Some craftspeople discovered that if they heated iron hot enough and hammered it repeatedly, they could shape it, joining pieces together through forge welding and slowly working the metal into useful forms. This process was extraordinarily labor-intensive and required maintaining the iron at just the right temperature, not so hot that it burned away or became too brittle, but hot enough to remain workable. Even when shaped successfully, meteoritic iron often proved unpredictable in its properties, sometimes brittle, sometimes tough, its behavior depending on its precise composition and the treatment it received. Meanwhile, all around the ancient world, there existed vast quantities of iron locked away in earthly ores. Iron is, in fact, one of the most abundant elements in the Earth's crust, far more common than copper or tin. But this iron remained invisible to those who searched for it, unlike copper ores, which often displayed distinctive green or blue colors that caught the eye of ancient prospectors. Iron ores could look deceptively ordinary. Some iron ores were simply rust-red rocks, others dark and heavy. But none announced their potential with the obvious visual signals that copper ores provided. Even when ancient peoples did heat iron-bearing rocks, perhaps by chance in their pottery kilns or copper smelting furnaces, the results were disappointing. At the temperatures used for copper smelting, iron ore does not produce a neat pool of liquid metal at the bottom of the furnace. Instead, it forms a spongy, porous mass mixed with slag and impurities, a material called a bloom. This bloom looked nothing like the clean ingots of copper or bronze that smelters expected. To someone unfamiliar with iron's peculiar behavior, this grey, crusty mass might simply be discarded as failed smelting, as worthless slag to be thrown onto the waste heap. Yet there were experimenters, patient observers, who noticed that within these unpromising blooms, there was something interesting happening. The spongy material, when reheated and hammered repeatedly, could be consolidated into a denser mass. The hammering drove out impurities, and with enough work, enough heating and striking, a piece of workable iron could emerge. This process was nothing like the elegant simplicity of casting bronze. It was exhausting, time-consuming work that required tremendous skill to judge temperatures and know exactly when and how to hammer the bloom. For centuries, perhaps even millennia, there were likely isolated instances of people creating small amounts of iron from earthly ores, experimental pieces that demonstrated the possibility without yet unlocking the full potential. Archaeological evidence suggests that in various places around the Near East, in Anatolia, in the Caucasus region, in Mesopotamia, people were conducting these experiments, slowly accumulating knowledge about this stubborn, difficult metal. The challenge was not merely technical, but also practical. Why invest enormous effort in learning to work with iron when bronze was available, reliable, and produced excellent tools and weapons? Bronze technology had reached sophisticated heights. The workshops hummed with productive activity. Trade networks supplied the necessary materials, and craftspeople understood their materials intimately. Iron, by contrast, promised only difficulty and uncertainty. What kept some metallurgists interested in iron, despite these obstacles, was the tantalizing glimpse of its potential. When iron was worked correctly, when it was hammered and reheated just so, it could be made harder than bronze. Those few pieces of well-worked iron that did emerge from experimental forges showed properties that bronze could not match. Iron's cutting edges when properly made, stayed sharp longer than bronze. Iron tools were less likely to bend under stress than their bronze counterparts. The meteoritic iron daggers and ornaments treasured by royalty demonstrated what might be possible if only earthly iron could be worked in quantity. But the path from understanding iron's promise to actually producing it reliably remained shrouded in mystery, hidden behind technical challenges that would require generations of persistent experimentation to overcome. The secret of iron lay waiting, not in distant lands or hidden mines, but in understanding how to coax this abundant but stubborn element from ordinary rocks into extraordinary usefulness. The mystery that had perplexed generations of metalworkers was finally beginning to yield its secrets. For centuries, iron had existed on the edges of human knowledge, a tantalizing material that promised something extraordinary, yet remained frustratingly difficult to master. The occasional meteoritic blade had demonstrated iron's potential, but transforming the reddish-brown stones found in hillsides and riverbeds into useful metal required a leap in understanding and technique that would take humanity more than 1,000 years to achieve. Somewhere around 1200 BCE, in the rugged highlands where Anatolia meets the Caucasus Mountains, metalworkers made the crucial breakthrough that would reshape human civilization. The exact location remains a matter of scholarly discussion, with evidence pointing to multiple sites across this region, where innovative craftspeople experimented with increasingly hot fires and new approaches to extracting metal from stubborn ore. Unlike the discovery of bronze, which may have happened accidentally when mixed ores were smelted together, ironworking required deliberate innovation and careful observation of processes that behaved quite differently from anything metalworkers had encountered before. The fundamental challenge lay in temperature. Copper melts at approximately 1085 degrees Celsius, a heat attainable in the improved furnaces of the Bronze Age. Iron, however, refuses to melt until temperatures reach about 1538 degrees Celsius, far beyond what any ancient furnace could achieve. This meant that the liquid metal techniques used for copper and bronze simply would not work. Metalworkers could not pour molten iron into molds or watch it pool at the bottom of their furnaces in shimmering puddles of promise. Instead, the iron smelting process that emerged required an entirely different approach. The breakthrough came from understanding that iron ore could be reduced to metal at temperatures well below its melting point through a process that modern metallurgists call solid-state reduction. When iron ore, typically hematite or magnetite, was heated to temperatures between 1100 and 1200 degrees Celsius in the presence of burning charcoal, a remarkable transformation occurred. The carbon monoxide produced by the burning charcoal would strip oxygen from the iron oxide in the ore, leaving behind particles of nearly pure iron. These iron particles would then sinter together, welding themselves into a spongy mass that ancient metalworkers called a bloom. The bloom was not pure iron, but rather a mixture of iron crystals interspersed with slag, the glassy waste material composed of impurities from the ore mixed with ash and other furnace residues. This bloom, still glowing hot from the furnace, had to be worked immediately. Metalworkers would place it on a sturdy stone anvil and strike it repeatedly with hammers, forcing out the liquid slag while consolidating the iron particles into a more solid mass. The furnaces developed for this process, known today as bloomery furnaces, represented sophisticated adaptations of existing metallurgical knowledge. These structures were typically built as cylindrical or domed chambers, constructed from clay or stone, carefully designed to contain intense heat while allowing controlled airflow. Some were built into hillsides to take advantage of natural drafts, while others incorporated bellows arrangements that grew increasingly elaborate as metalworkers refined their techniques. The Hittite civilization, centered in Anatolia during the late Bronze Age, appears prominently in the early iron story. Archaeological evidence and fragmentary texts suggest the Hittites were among the first peoples to develop reliable iron smelting techniques. Their empire, which flourished during the second millennium BCE, controlled regions rich in iron ore. Letters from Hittite rulers mention iron gifts sent to neighboring kings, suggesting the metal remained rare and precious, even as production techniques improved. What made iron smelting particularly challenging was the precise control required throughout the process. The furnace needed to be hot enough to reduce the ore, but not so hot that the iron absorbed too much carbon from the charcoal, which would make it brittle. The ratio of ore to charcoal, the flow of air through the furnace, the duration of the heating, and the timing of the bloom extraction all affected the quality of the final product. Metalworkers had to learn through patient experimentation and careful observation, gradually building up a body of knowledge that could be passed from master to apprentice. The air supply proved critical to success. Too little air, and the furnace would not reach the necessary temperature. Too much, and the iron might oxidize back into useless scale or absorb excessive carbon. Some regions developed taller furnace structures that created stronger natural drafts, while others refined their bellows technology using leather bags operated by foot or by hand to force carefully measured airflows into the burning chamber. The physical effort required for iron production far exceeded that of bronze working, where bronze could be melted and poured with relative ease. Iron demanded hours of sustained high temperatures, followed by intense physical labor to forge the bloom into usable metal. A single bloom might require hundreds of hammer blows while still red hot, with the metalworker repeatedly reheating the mass to keep it workable. This labor-intensive process meant that early iron production remained small-scale, with individual smiths producing modest quantities of metal from furnaces that might yield only a few kilograms of iron from each smelting operation. Yet despite these challenges, the knowledge slowly spread and improved as metalworkers shared techniques, either through trade contacts, the movement of skilled craftspeople, or perhaps through the observation of captured smiths. The quality and consistency of iron production gradually increased. Each generation of metalworkers built upon the discoveries of their predecessors, learning which ores worked best, which furnace designs produced the most reliable results, and which techniques yielded the strongest iron. The breakthrough around 1200 BCE did not mean iron immediately flooded across the ancient world. The technology remained difficult, and the production capacity limited. Bronze continued to dominate for weapons, tools, and artistic works in most regions for centuries after iron smelting became possible. But the door had been opened. The secret of transforming common brown rocks into a metal harder than bronze was no longer beyond human capability. The Iron Age had not yet fully dawned, but the long night of mystery was ending, and the first light of a new metallurgical era was breaking across the ancient world. The secret of ironworking, once unlocked in the highlands of Anatolia and the mountains of the Caucasus, began its journey outward like ripples spreading across a vast pond. This knowledge would travel slowly at first, carried by traders, wandering smiths, and migrating peoples across landscapes that stretched from the Mediterranean shores to the distant reaches of Asia and southward into the heart of Africa. The spread of iron technology would unfold over centuries, transforming societies as it moved, yet taking remarkably different paths depending on geography, resources, and the unique circumstances of each culture it touched. From its origins around 1200 BCE, iron-working knowledge moved gradually westward into Greece and the Mediterranean world. The collapse of Bronze Age civilizations in this period, sometimes called the Bronze Age collapse, may have actually facilitated the spread of iron technology. As old trade networks fragmented and tin became scarce, the motivation to master ironworking grew stronger. Greek smiths began establishing their own traditions of ironworking, developing techniques suited to local ores and needs. By 1000 BCE, iron tools and weapons were becoming increasingly common throughout the Greek world, though bronze still retained prestige for certain ceremonial purposes. The technology continued spreading into Europe through multiple routes, and knowledge traveled along trade routes that had once carried tin and copper. Other transmission occurred through the movement of Celtic peoples who became masterful ironworkers and spread their techniques across wide territories. By 800 BCE, ironworking had reached Central Europe, and skilled craftspeople were establishing forges in regions rich with iron ore. The forests of Europe provided abundant charcoal for smelting, making iron production particularly viable in lands where copper and tin had been scarce. Southward from Anatolia, ironworking knowledge reached Egypt. Though the Egyptians adopted the new technology relatively slowly, their abundant access to copper through Sinai mines and well-established bronze working traditions meant less urgency to master the more challenging iron smelting process. Nevertheless, by around 600 BCE, iron had become the dominant metal for tools and weapons in Egypt as well, as the practical advantages eventually overcame traditional preferences. The spread of iron technology into sub-Saharan Africa followed fascinating and sometimes independent paths. While some ironworking knowledge may have traveled southward from Phoenician colonies in North Africa or through Egyptian connections, evidence suggests that certain African societies may have developed ironworking independently or nearly so. The knot culture of modern-day Nigeria was producing iron by around 500 BCE, creating both practical tools and remarkable terracotta sculptures. Some scholars have proposed even earlier dates for African ironworking, though the evidence remains debated. What is certain is that African smiths developed their own distinctive furnace designs and smelting techniques, particularly well adapted to local ores and conditions. In East Africa, ironworking spread through the Great Lakes region and southward, with the Bantu expansion carrying metallurgical knowledge across vast distances. Interestingly, many African societies transitioned directly from stone tools to iron implements, largely bypassing the Copper and Bronze Ages that characterized development elsewhere. This direct leap to iron technology would shape African metallurgical traditions in unique ways, as craftspeople developed techniques without the intermediate experience of working softer metals. Eastward from the Caucasus and Near East, iron-working knowledge traveled along the same trade routes that had once carried lapis lazuli, textiles, and precious metals. The technology reached Persia and gradually spread into Central Asia. Persian smiths became highly skilled in ironworking, developing distinctive styles and techniques that would later influence Islamic metallurgical traditions. In India, ironworking appeared by approximately 1000 BCE, possibly through contact with the Middle East, though some researchers have suggested independent development. Indian metallurgists would eventually become renowned for their exceptional iron and steelworking skills. Ancient Indian texts called the Vedas make references to iron, using the term shyama ayas, or dark metal, distinguishing it from copper. Indian smiths demonstrated remarkable skill in producing large iron objects, including the famous Iron Pillar of Delhi, erected around 400 CE, which stands over 7 meters tall and has resisted rusting for more than 16 centuries. A testament to the purity of iron achieved by ancient Indian metallurgists. The arrival of iron technology in China represents one of the most intriguing chapters in metallurgical history. Ironworking appeared in China somewhat later than in the West, around 600 BCE, but Chinese metallurgists brought their own innovative approaches to working this metal. Drawing on their already advanced bronze casting traditions, Chinese smiths developed techniques quite different from those used in the West. While Western ironworking focused on the bloomery process, producing wrought iron, Chinese metallurgists developed blast furnace technology earlier than other cultures, allowing them to produce cast iron at scale. The spread of ironworking to the Korean peninsula and Japan came later still, reaching these regions around 300 BCE. Japanese smiths would eventually develop their own highly refined traditions, though these would flourish more fully in later centuries. The volcanic islands of Japan contained iron sand deposits that required adapted smelting techniques, leading to the development of distinctive Japanese furnace designs. Across these vast geographical expanses, each culture adapted ironworking to suit local conditions, available resources, and existing craft traditions. Some regions had easy access to high-quality ores that smelted readily, while others worked with more challenging materials requiring innovative solutions. Forest-rich areas could produce charcoal abundantly, while other regions needed to develop more fuel-efficient furnace designs. Coastal peoples might trade for ore or finished iron, while continental societies developed local mining operations. The pace of adoption varied tremendously. Some societies embraced iron technology rapidly, recognizing its advantages and investing in developing the necessary infrastructure and skills. Others maintained bronze working traditions alongside iron for extended periods, using each metal for purposes to which it was best suited. A few isolated societies would not encounter ironworking until much later, continuing with stone, bone, and wood technologies into recent centuries. What united these diverse ironworking traditions was the fundamental challenge of the material itself. Everywhere iron was worked, smiths needed to master the art of achieving sufficient heat, controlling the smelting process, and repeatedly hammering the bloom to consolidate the iron and remove impurities. These core techniques, first discovered in Anatolia and the Caucasus, formed the foundation upon which each culture built its own metallurgical tradition. The spread of ironworking knowledge represents not just the transmission of technical information, but the human capacity to adapt, innovate, and improve upon inherited wisdom, creating something suited to each unique time and place. As ironworking knowledge spread across continents and settled into the daily rhythms of countless communities, people began to understand something curious about this new metal. It was not simply a replacement for bronze, not merely another material that could serve the same purposes. Iron revealed itself to be something different entirely, a substance with its own character, its own promises, and its own peculiar demands. The first thing any smith noticed was weight. An iron tool felt different in the hand than its bronze counterpart. There was a certain heft, a density that spoke of substance and strength. A farmer holding an iron plough blade for the first time could sense something fundamental about the material before ever putting it to work in the soil. This was a metal that meant business, metal that carried authority in its very mass. But weight alone did not explain iron's gradual conquest of the ancient world. The real story lay in abundance. Bronze required two metals brought together: copper and tin. In many regions, particularly tin, these materials had to travel vast distances along fragile trade routes. A disruption in commerce could leave a smith without materials, a kingdom without weapons, a civilization vulnerable. Iron ore, by contrast, seemed to hide everywhere. The reddish-brown stones that yielded iron could be found in hills and valleys across nearly every landscape. A community with the knowledge to smelt iron need not depend on distant traders or worry that foreign powers might cut off their supply. This abundance meant something profound for societies making the transition. Bronze had been, in many ways, a metal of the elite. The expense of acquiring tin and copper, the specialized knowledge required for alloying, the established trade networks controlled by powerful interests. All of this made bronze weapons and tools markers of status and power. Iron democratized metallurgy. A village far from trade routes could establish its own smelting operation. Farmers could afford iron tools where bronze had remained beyond their means. Armies could equip common soldiers with iron weapons rather than reserving metal armaments for aristocratic warriors alone. Yet iron did not surrender its gifts easily. The very process of smelting iron presented challenges that humbled smiths accustomed to working bronze. Bronze melted into liquid that could be poured into molds, flowing into intricate shapes with the smooth cooperation of a substance eager to please. Iron, heated in the furnaces of the early Iron Age, never quite melted. Instead, it formed a spongy, porous mass called a bloom, a lump of material riddled with impurities and slag that had to be hammered out through patient, exhausting work. The smith would extract this bloom from the furnace while it still glowed with heat, then begin the long process of consolidating the metal. Hammer blows would squeeze out slag, force the iron particles to weld together, gradually transform the spongy mass into something solid and workable. This was labor that required strength, timing, and an intuitive understanding of how the metal behaved at different temperatures. A bronze smith could cast multiple items in a day. An iron smith might spend days working a single bloom into usable material. And even then, the resulting iron often disappointed. In its simplest form, wrought iron was softer than bronze. It could bend when bronze would have held its edge. A sword of pure wrought iron might fail in combat against a bronze blade. A considerable irony, given the effort required to produce it. Many communities that first acquired ironworking knowledge must have wondered whether the struggle was worthwhile. The answer lay in a secret that iron kept hidden, revealed only to those who continued to experiment and observe. Iron, unlike bronze, could be transformed through a process called carburization. When iron was heated in contact with carbon, from charcoal, from burning wood, from the very fires used to work it, something remarkable occurred. The iron absorbed carbon, and this marriage of elements created a new material with properties that exceeded bronze in nearly every measure. The process happened gradually, almost invisibly. A smith heating iron in a charcoal forge might notice that the surface of the metal seemed to harden, that it took a keener edge, that it resisted wear more stubbornly than before. The mechanism remained mysterious to ancient craftspeople, but the effect was undeniable. They learned through countless cycles of trial and observation that prolonged heating in the forge, particularly when the iron was packed in charcoal, produced superior results. This carbonized surface layer, though thin, gave iron tools and weapons their essential advantage. A blade with a carburized edge would hold its sharpness longer than bronze, would maintain its integrity through hard use, would require less frequent resharpening. The difference might seem minor in abstract description, but to a farmer working long days in the field, or a soldier whose life depended on his weapon's reliability, it meant everything. Different regions discovered various approaches to carburization, each culture developing techniques suited to their particular circumstances and traditions. Some smiths learned to repeatedly fold and hammer iron, creating layers that distributed carbon more evenly through the metal. Others experimented with the duration and temperature of heating, finding optimal conditions for carbon absorption. Still others discovered that quenching hot iron in water or oil could lock in hardness, though the metal became more brittle in the process. A trade-off that required careful judgment depending on an object's intended use. These techniques developed slowly, incrementally, across generations of craftspeople. Each smith built upon the accumulated knowledge of predecessors, sometimes making intuitive leaps that improved the process, sometimes passing along misunderstandings that later smiths would have to unlearn. The oral transmission of metalworking knowledge meant that techniques could be refined or corrupted as they spread, leading to regional variations in practice and quality. The superior edge retention of carburized iron tools revolutionized agriculture in ways that rippled through entire societies. A plow blade that stayed sharp longer meant more land, or could be cultivated before stopping to sharpen or replace the implement. An iron axe that held its edge through the day meant forests could be cleared more efficiently, opening new land for settlement. Iron sickles and scythes made harvest work less laborious, allowing smaller populations to gather larger crops. For warfare, the implications were equally transformative. as iron weapons became more common and techniques improved. Armies gradually transitioned from bronze to iron armaments. The process took centuries and happened unevenly, with some regions clinging to bronze traditions long after others had embraced iron. But the trajectory was clear. Iron's abundance meant armies could be larger. Its hardness, when properly worked, meant weapons could be more effective. The civilization that mastered iron metallurgy gained advantages that bronze-working societies found increasingly difficult to counter. Yet challenges remained. Iron rusted in ways bronze did not, requiring maintenance and care to prevent deterioration. The quality of iron varied dramatically depending on the skill of the smith and the particular ore used. A poorly made iron tool might indeed perform worse than bronze, and many communities struggled through long periods of producing mediocre iron before their crafts. People mastered the necessary techniques. As smiths continued their patient work at forges across the ancient world, as they experimented with heating and hammering and quenching, as they discovered the transformative power of carbon, they were setting the stage for even greater discoveries that lay ahead in the continuing story of humanity's relationship with iron and its remarkable potential. The iron that early smiths coaxed from their furnaces was not yet the material that would dominate the ages to come. It emerged from the bloomery as a spongy, irregular mass riddled with impurities and inconsistencies. Each piece behaved differently under the hammer, some areas harder than others, some more brittle, some refusing to hold an edge, no matter how carefully shaped. The blacksmiths of the early Iron Age knew they possessed something valuable, yet tantalizingly imperfect. The metal that came from their fires held tremendous promise, but unlocking its full potential would require generations of patient experimentation and careful observation. In workshops from Anatolia to India, from the valleys of China to the forests of northern Europe, craftspeople began the slow work of understanding iron's temperament. They noticed that iron fresh from the furnace was soft and malleable, easily worked, but not particularly useful for tools that needed to cut or pierce. They discovered that repeated heating and hammering not only shaped the metal, but changed its very nature, driving out some impurities and consolidating the mass into something more uniform and dependable. This process of folding and welding, heating and hammering, became a meditative ritual as much as a practical technique. The bloomery furnace itself became a subject of continuous refinement. Smiths experimented with different heights, seeking the perfect balance between airflow and heat retention. They tried various combinations of charcoal and ore, learning through countless attempts which ratios produced the most workable iron. The bellows grew larger and more sophisticated, some cultures developing foot-powered designs, while others harnessed water wheels to drive air into the burning heart of the furnace. Each improvement in temperature control brought better results, though the variations from one firing to the next remained frustratingly unpredictable. Some smiths began to notice that iron kept longer, in contact with burning charcoal, took on different qualities. The surface seemed harder, more resilient, capable of holding a sharper edge. What they were witnessing, though they could not name it, was the absorption of carbon from the charcoal into the iron's surface. This carburization process happened slowly, almost imperceptibly. Yet it made all the difference between a tool that remained serviceable and one that became treasured. The discovery was not a single moment of revelation, but rather an accumulation of observations across many lands and many years. In the Indian subcontinent, metallurgists developed particularly refined techniques for producing superior iron. They learned to select ores with great care, understanding that not all iron-bearing stones yielded equally good results. Their furnaces were built with meticulous attention to proportion, and they controlled their fires with a precision that allowed them to produce iron of remarkable consistency. Some regions became famous for their iron, with communities developing specialized knowledge passed from master to apprentice in closely guarded traditions. Chinese smiths approached the challenge from a different direction, building taller furnaces that could reach higher temperatures. They discovered that at sufficient heat, iron would actually melt and flow, creating what we now call cast iron. This material was too brittle for swords or tools that needed to flex, but it proved excellent for vessels, agricultural implements, and architectural elements. The Chinese experimented with ways to reduce the carbon content of cast iron through repeated heating and working, creating a path to better iron that differed markedly from Western techniques. Across the Mediterranean world and into Europe, the quality of iron varied considerably from one region to another. Some areas were blessed with particularly pure ores that yielded good iron with relative ease. Others struggled with ores containing sulfur or phosphorus, elements that made the resulting metal weak or brittle. Smiths learned to recognize the subtle differences in their raw materials, developing a practical knowledge of geology without understanding the underlying chemistry. They traded information as well as goods, sharing observations about which stones produced the best metal and which techniques yielded the most reliable results. The development of quenching techniques marked another significant advance in ironworking. Smiths discovered that plunging hot iron into water or oil could dramatically increase its hardness. The rapid cooling trapped the metal in a particular state, creating a hardness that slow cooling never achieved. However, this hardness came with brittleness, and craftspeople learned to follow quenching with careful tempering, gently reheating the metal to reduce brittleness while retaining most of the hardness. The colors that danced across heating iron became a guide, each hue indicating a different temperature and resulting property. Different cultures developed distinctive approaches to improving their iron. Celtic smiths in Europe became renowned for their skill in pattern welding, twisting together rods of iron with different properties and forging them into a single blade. The resulting weapons combined hard edges with flexible cores, and the distinctive patterns on the finished pieces became badges of superior craftsmanship. In Japan, though ironworking arrived later, smiths would eventually develop elaborate folding techniques that purified and refined their metal through repeated welding and hammering. The furnaces themselves continued to evolve, growing taller and more efficient with each generation. Some communities built permanent stone structures that served for years, while others constructed temporary furnaces for each smelting operation. The knowledge of how to build and operate these furnaces became valuable expertise, and skilled furnace masters could command respect and compensation throughout the ancient world. They understood the subtle adjustments of air and fuel, the precise moments to add ore, and the signs that indicated when the bloom was ready to be withdrawn. As centuries passed, the accumulated knowledge of countless experiments began to yield more consistent results. Iron implements became increasingly reliable, no longer the unpredictable products of an uncertain process. Smiths developed intuitions about their craft that they could not fully articulate, but which guided their hands with increasing confidence. The gap between the best iron and the worst gradually narrowed as techniques improved and spread across trading networks and cultural boundaries. Yet even as ironworking became more refined, smiths knew they had not yet achieved the ultimate potential of their material. They had seen occasional pieces emerge from their forges with exceptional properties, harder and more resilient than typical iron, capable of holding edges that seemed almost magical in their sharpness and durability. These rare successes hinted at something beyond ordinary iron, a superior material that existed more by accident than design. Understanding how to create this remarkable substance deliberately rather than accidentally would become the next great challenge, one that would lead to the development of true steel and transform the capabilities of human civilization once again. The gradual improvements in ironworking had brought humanity to the threshold of something remarkable. Across the ancient world, from the workshops of the Mediterranean to the forges of Asia, craftspeople had learned to coax better and better qualities from their iron. Yet the best iron still had its limitations, and the pursuit of something superior continued to drive innovation in workshops where glowing metal met human ingenuity. The secret lay hidden in something invisible, something that ancient metallurgists could not see, but could nevertheless control through careful observation and practice. Carbon, that fundamental element that exists in charcoal and coal, held the key to transforming ordinary iron into a material of extraordinary strength and resilience. When iron absorbed just the right amount of carbon during heating, it became steel, a substance that combined the best qualities of both iron and bronze while surpassing them both. The earliest steel production emerged not from a single moment of discovery, but from the gradual refinement of techniques across multiple civilizations. In the Indian subcontinent, perhaps as early as the 6th century before the Common Era, smiths developed methods for creating remarkably pure steel through careful heating and hammering. They discovered that by repeatedly folding and forging iron while it remained in contact with carbon-rich materials, they could drive carbon into the metal's very structure, creating a product of exceptional quality. These Indian craftspeople worked in an environment where temperature control became an art form in itself. They learned to read the colors of heated metal with extraordinary precision, understanding that the subtle shift from cherry red to orange yellow could mean the difference between success and failure. The iron blooms they started with were carefully selected, then subjected to heating cycles that could last for hours or even days. During this time, the metal would absorb carbon from the charcoal surrounding it, gradually transforming its internal character. In China, metallurgists approached the challenge from a different direction. Their mastery of high-temperature furnaces, developed for casting bronze and later iron, gave them unique capabilities. Chinese smiths discovered methods of creating steel through co-fusion, melting wrought iron together with cast iron to produce a material with intermediate carbon content. This technique, which appeared during the Han Dynasty, represented a sophisticated understanding of how different forms of iron could be combined to achieve desired properties. The Chinese also developed crucible steel techniques, sealing small amounts of wrought iron with organic materials in clay containers and heating them for extended periods. Inside these sealed environments, protected from oxygen and impurities, the iron slowly absorbed carbon, transforming into steel of remarkable consistency. The patience required for such processes speaks to the dedication of ancient craftspeople who might tend their furnaces through day and night, maintaining precise conditions for the transformation to occur. In the Middle East and Persia, similar explorations yielded their own varieties of steel. The cementation process, which involved packing iron bars in sealed containers with carbon-rich materials, allowed smiths to create steel through prolonged heating. These techniques spread along trade routes, carried by traveling craftspeople and merchants who recognized the value of superior metal. Each region adapted the basic principles to their available materials and existing traditions, creating variations in technique that nonetheless shared common underlying principles. The production of ancient steel required resources beyond simple materials. Furnaces needed to maintain steady, intense heat for hours at a time. This demanded substantial quantities of fuel and often required multiple workers to operate bellows or tend fires. The knowledge itself became a precious commodity, passed down through apprenticeship and guarded as valuable trade secrets. Master steelmakers earned respect and patronage from rulers who understood that superior weapons and tools could determine the fate of kingdoms. The properties of steel, even in these ancient forms, were immediately apparent to those who worked with it. A steel blade could hold a sharper edge than iron and maintain that edge through rigorous use. Steel tools proved more resistant to damage and wear, lasting longer and performing better than their iron counterparts. The slight flexibility of properly made steel meant that swords and knives were less likely to shatter or bend permanently under stress, qualities that made them invaluable for both craftspeople and warriors. Yet producing steel consistently remained challenging throughout antiquity. The carbon content had to fall within a relatively narrow range. Too little, and the metal behaved like ordinary iron. Too much, and it became brittle like cast iron. Ancient metallurgists had no chemical tests, no precise measurements, only their trained senses and accumulated experience. They learned to judge their success by the appearance of the metal's grain when broken, by the sound it made when struck, by the way it responded to hammering and heating. Different applications demanded different qualities, and skilled steelmakers learned to adjust their techniques accordingly. Steel for cutting tools needed to be harder, able to take and hold a very fine edge. Steel for springs or flexible implements required different properties, combining strength with the ability to bend and return to shape. The most accomplished smiths could produce steel tailored to specific purposes, adjusting their processes through subtle changes in heating time, cooling methods, and the amount of working the metal received. The rarity and expense of steel meant that it often appeared in smaller quantities, used for the business end of tools where its superior properties mattered most. An axe might have a steel blade welded to an iron body, combining the economics of abundant iron with the performance of precious steel. Knives and swords might feature steel edges, forge welded to iron cores, creating composite blades that balanced different properties in a single implement. As generations passed, the body of knowledge surrounding steel production grew richer and more nuanced. Smiths discovered that heating steel and then cooling it rapidly in water or oil made it harder but more brittle, while slowly cooling it in air produced a tougher but softer result. They learned that reheating hardened steel to moderate temperatures and then cooling it, a process later called tempering, could reduce brittleness while retaining much of the hardness. These discoveries emerged from countless experiments, from both successes and failures in workshops scattered across continents. The steel produced in these ancient times, though limited in quantity, began to establish reputations that would echo through history. Certain regions became known for their exceptional steel, drawing merchants from distant lands. The ingots and bars of steel became trade goods in their own right, traveling along the same routes that carried silk, spices, and precious metals. And somewhere in this network of knowledge and commerce, the stage was being set for the emergence of legendary materials that would capture imaginations for centuries to come. The trade routes connecting the ancient world carried many precious commodities, but few were as sought after as the steel ingots that traveled from the workshops of southern India. These cylindrical cakes of metal, each small enough to fit in a person's hand, contained within them a secret that metallurgists across Asia and Europe would spend centuries trying to unravel. The steel produced in India through the crucible method had earned a reputation that spread from the Mediterranean to East Asia, and its journey from raw material to finished masterpiece tells one of metallurgy's most fascinating stories. In the regions of southern India, particularly around Hyderabad, metallurgists had perfected a technique for producing steel that would become known as Wootz. The process began with carefully selected iron ore and specific types of wood that provided not just heat, but particular characteristics to the finished product. The craftspeople would place small pieces of wrought iron into clay crucibles, along with carbonaceous materials, sometimes including leaves or wood chips from particular trees that generations of experience had identified as ideal for the purpose. These sealed crucibles would then be subjected to intense heat in specialized furnaces for several hours. What happened inside those sealed vessels was a slow, careful dance of chemistry and temperature. The iron would absorb carbon from the organic materials, but unlike the carburization techniques used elsewhere, the crucible method allowed for exceptional control and uniformity. The metallurgists had learned to maintain temperatures high enough to partially melt the iron, creating a liquid state that allowed the carbon to distribute evenly throughout the metal. When the crucibles cooled and were broken open, they revealed small ingots of steel with a very particular internal structure. The Wootz ingots themselves were unremarkable in appearance, simple discs or cylinders of dark metal, but their internal composition was extraordinary. The slow cooling process and the precise carbon content created a microstructure of iron carbides distributed in specific patterns through the softer iron matrix. This internal architecture, invisible to the eye in the raw ingot, would only reveal itself when the steel was forged and etched, producing the distinctive watered patterns that would later make Damascus steel legendary. These ingots became valuable trade goods, traveling westward along established commercial routes. Arab and Persian merchants recognized the superior quality of Indian steel and transported the ingots to metalworking centers throughout the Middle East. The city of Damascus in Syria emerged as one of the most renowned locations where craftspeople transformed these precious ingots into finished blades. The swordsmiths of Damascus developed their own closely guarded techniques for working the Wootz steel, forging the ingots at specific temperatures and with particular patterns of hammering that enhanced the metal's natural properties. The forging process for what became known as Damascus steel required both skill and patience. The smiths would heat the Wootz ingots carefully, avoiding temperatures that were too high, which could destroy the special carbide structures within the metal. Through repeated heating and hammering, they would draw out the ingots into long blades, each hammer blow aligning and refining the internal structure. The resulting swords combined exceptional hardness with surprising flexibility, able to hold extraordinarily sharp edges while resisting the brittleness that plagued lesser steels. But perhaps the most celebrated feature of Damascus steel blades was their appearance. When the finished blade was polished and treated with acidic solutions, remarkable patterns would emerge on the surface. These patterns, resembling flowing water, wood grain, or even ladders and roses, were not decorative additions but natural manifestations of the steel's internal structure. The carbide bands and the boundary between different crystal structures created these distinctive markings, and no two blades were ever exactly alike. The patterns served as proof of authenticity and quality, visual evidence that the blade had been forged from genuine Wootz steel. The reputation of these blades spread across the medieval world. Warriors from Europe to Central Asia prized Damascus steel weapons for their performance in use. Accounts from the Crusades describe European knights encountering blades that could supposedly cut through their own swords or slice falling silk scarves, though such stories likely mingled fact with admiration and legend. What is certain is that Damascus steel represented the pinnacle of blade-making technology for its era, a standard that other metallurgical traditions struggled to match. The knowledge required to produce both Wootz and Damascus steel remained concentrated in specific regions and workshops, passed from master to apprentice through direct demonstration and experience. The Indian crucible steelmakers guarded their techniques, understanding that their expertise provided both livelihood and status. Similarly, the Damascus smiths maintained secrecy around their forging methods. This concentration of knowledge meant that the steel remained expensive and somewhat rare, accessible primarily to wealthy patrons and important military figures. Different regions developed their own relationships with this legendary steel. Persian smiths created their own variations, sometimes using locally produced crucible steel or adapting their forging techniques to the Wootz they imported. In some areas of Central Asia, metallurgists experimented with pattern welding techniques that could create visually similar effects to Damascus steel, though the underlying structure and properties differed. The Japanese heard tales of this Western steel, even as they were developing their own sophisticated methods for creating exceptional blades from their particular iron sources. The trade in Wootz ingots and Damascus blades represented more than simple commerce. It was an exchange of technological achievement, cultural values, and artistic vision. The steel connected the craftspeople of southern India with the smiths of the Middle East, the merchants who transported the goods, and the warriors and collectors who ultimately used and treasured the finished products. Each ingot that traveled westward carried with it centuries of accumulated metallurgical knowledge, even if the end users could never fully understand the processes that had created the steel they valued so highly. For modern metallurgists studying historical samples of Wootz and Damascus steel, the material reveals a sophistication that challenges assumptions about ancient technology. Analysis shows the presence of carbide structures and even trace elements like vanadium that contributed to the steel's properties. The question of exactly how ancient craftspeople achieved such precise control without modern instruments or theoretical understanding continues to inspire both admiration and research. The steel stands as testament to what careful observation, patient experimentation, and accumulated experience could achieve, even without the framework of modern material science. As you drift towards sleep tonight, you might picture those small clay crucibles in their furnaces, glowing with heat, as carbon slowly diffused into iron, creating something greater than the sum of its parts. The rhythmic hammer blows of Damascus smiths echo across centuries, each strike refining and revealing the hidden patterns within the steel, transforming simple ingots into legendary blades whose reputation would outlast empires. The story of metallurgy now carries us eastward, across vast mountain ranges and endless steppes, to the ancient lands of China, where metallurgists followed paths distinctly their own. While Western smiths had perfected their techniques with Wootz and Damascus steel, Chinese craftspeople were developing innovations that would prove equally revolutionary, yet startlingly different in their approach and execution. In the valleys of the Yellow River, where civilization had flourished for thousands of years, Chinese metallurgists faced the same fundamental challenges as their counterparts elsewhere in the world. They needed stronger metals for tools, weapons, and the countless implements of daily life. But the solutions they discovered would diverge from Western methods in fascinating ways, creating a parallel tradition of metalworking that would eventually contribute its own essential wisdom to humanity's understanding of metals. Perhaps most remarkable among China's metallurgical achievements was the early development of blast furnace technology. While European smiths would not master this technique for many centuries to come, Chinese metallurgists were operating true blast furnaces as early as the 5th century before the Common Era. These were not the small bloomery furnaces common elsewhere, which produced spongy masses of iron that required extensive hammering and reheating. Instead, Chinese furnaces achieved temperatures high enough to fully melt iron, allowing it to be cast into molds much like bronze. The secret lay partly in the construction of these remarkable furnaces. Chinese metallurgists built tall cylindrical structures, sometimes reaching heights of several meters, constructed from heat-resistant clay and stone. The increased height created a stronger draft, and the continuous operation allowed the furnace interior to reach extraordinary temperatures. Bellows, often powered by water wheels along China's many rivers, forced air into the furnace base with relentless efficiency. This combination of design and power enabled temperatures that caused iron ore not merely to reduce to solid metal, but to fully liquefy. This molten iron could then be poured into prepared molds, creating cast iron objects of considerable size and complexity. Agricultural implements, cooking vessels, construction materials, and even ornate decorative pieces flowed from these furnaces in quantities that would have astonished Western smiths of the same era. The ability to cast iron into precise shapes eliminated much of the laborious hammering and forging that characterized ironworking elsewhere in the world. But cast iron, for all its advantages in ease of production, presented its own challenges. The high carbon content that made iron flow in liquid form also made it brittle and prone to cracking under stress. Cast iron cooking pots might serve admirably but cast iron swords would shatter in combat. Chinese metallurgists therefore developed sophisticated techniques to address these limitations, creating methods to control and modify the properties of their iron. One ingenious solution involved a prolonged heating process that allowed excess carbon to burn away from cast iron, gradually transforming it into wrought iron with properties more suitable for tools requiring strength and flexibility. This decarburization process required patience and careful attention, but it allowed Chinese craftspeople to start with easily produced cast iron and refine it according to their needs. Chinese steelmaking followed yet another distinctive path. While Indian smiths had perfected their crucible methods and Middle Eastern craftspeople had developed Damascus steel through forge welding, Chinese metallurgists developed their own techniques for creating steel. Some methods involved stacking alternating layers of cast iron and wrought iron, then forge welding them together through repeated heating and hammering. The carbon from the cast iron would gradually diffuse into the wrought iron, creating a steel with intermediate properties that combined the best qualities of both materials. The co-fusion process represented another Chinese innovation, where pieces of cast iron and wrought iron were melted together in a crucible, allowing them to combine into steel. This technique required precise control of temperature and timing, knowledge that skilled metallurgists guarded carefully and passed down through generations of craftspeople. Chinese bronzeworking also achieved remarkable sophistication, particularly during the Shang and Zhou dynasties. The bronze vessels created during these periods display technical mastery that rivals any bronze work produced anywhere in the ancient world. These were not simple castings, but complex pieces often created using piece mold casting techniques that allowed for intricate surface decoration and precise dimensional control. The metallurgists would carve designs into clay mold sections, assemble them around a core, and then pour molten bronze into the gap between core and mold. The resulting vessels, with their elaborate surface patterns and reliable uniformity, served both practical and ceremonial purposes across Chinese society. The organization of metalworking in ancient China also differed from patterns common in the West. Large-scale government operations often controlled significant metal production, particularly for military purposes. Imperial workshops employed hundreds of specialized workers, each focusing on particular aspects of the metallurgical process. Ore roasting, smelting, casting, and finishing might all be handled by different groups of craftspeople, creating an early form of assembly line production that achieved impressive efficiency and output. Yet alongside these official operations, countless smaller workshops served local communities, producing the everyday items that sustain Chinese civilization. Family workshops passed techniques from parent to child across generations, accumulating subtle refinements in method and practice. Regional variations developed as different areas adapted general principles to local conditions, available materials, and specific needs. The philosophical traditions of ancient China also influenced metallurgical practice in ways both practical and symbolic. The careful observation of natural processes that characterized Chinese philosophy encouraged metallurgists to work with materials rather than forcing them into predetermined shapes. The concept of transformation through controlled processes aligned perfectly with the metallurgist's work of turning ore into metal, metal into alloys, and raw castings into finished implements. Trade along the Silk Road and maritime routes eventually allowed some exchange of metallurgical knowledge between East and West, though the full extent of mutual influence remains a subject of scholarly investigation. Chinese steel found its way to distant markets, admired for its quality, even if the production methods remained mysterious to foreign buyers. Similarly, techniques and materials from the West occasionally reached Chinese workshops, where they might be adapted, refined, or incorporated into existing practices. As centuries passed, Chinese metallurgy continued evolving, always building on the distinctive foundations established in these early periods. The emphasis on cast iron production, the sophisticated approaches to steel making, and the organizational methods for large-scale metal production would all contribute to China's technological capabilities for generations to come. These innovations represented not merely different techniques, but different ways of thinking about metals and their possibilities, adding essential chapters to humanity's growing understanding of these remarkable materials. As the knowledge of ironworking matured across Asia and gradually made its way westward, Europe found itself embracing this transformative technology during what we now call the medieval period. The centuries between roughly 500 and 1500 CE witnessed a quiet but profound evolution in how European craftspeople worked with metals, building upon ancient foundations, while developing their own distinctive approaches to the art of metallurgy. The landscape of medieval Europe became dotted with forges, their chimneys sending plumes of smoke into misty valleys and along winding rivers. Unlike the great centralized workshops of some Eastern empires, European metalworking took on a more distributed character, with smiths establishing themselves in towns and villages across the continent. Each region developed its own reputation for particular types of metalwork, from the swordsmiths of Toledo in Spain to the armorers of Milan in Italy, from the cutlers of Solingen in Germany to the bell founders of the Low Countries. The medieval smith occupied a special place in society, respected for knowledge that seemed almost magical to ordinary people. The transformation of dull rock into gleaming metal, the ability to make iron bend to human will, the secret processes that could turn soft iron into hard steel. All of this marked the metalworker as someone who possessed extraordinary skills. Young apprentices would spend years learning the craft, beginning with simple tasks like maintaining the fire and gradually progressing to the mysteries of tempering and welding. One of the most significant innovations of the medieval period came not from a new understanding of the metal itself, but from a new source of power. European craftspeople began harnessing the energy of flowing water to drive their equipment, a development that would dramatically increase the scale and efficiency of metalworking. Water wheels, turning steadily in streams and rivers, could power massive bellows that pushed air into furnaces with far greater force and consistency than human-powered alternatives. The higher temperatures these mechanical bellows produced allowed for better smelting and more efficient forging. These same water wheels also drove trip hammers, heavy mechanical hammers that could strike iron repeatedly with tremendous force. A single water-powered trip hammer could accomplish in hours what might take a smith days of exhausting labor with a hand hammer. The rhythmic pounding of these mechanical hammers became a familiar sound near rivers throughout Europe, a steady beat that spoke of industry and progress. Ironworks began clustering along waterways where this power source flowed reliably, and certain regions became centers of production precisely because their geography offered abundant water power. The organization of metalworking in medieval Europe followed the guild system, carefully structured associations of craftspeople that controlled training, quality, and trade practices. These guilds guarded their knowledge carefully, passing techniques from master to apprentice through years of hands-on instruction rather than written texts. A young person entering the metalworking trade would first serve as an apprentice, perhaps for 7 years or more, learning basic skills while living in the master's household. After completing this apprenticeship, they might become a journeyman, traveling to work with different masters and learning regional variations in technique. Only after producing a masterpiece, a demonstration piece showing exceptional skill, could they hope to become a master craftsperson themselves and perhaps establish their own workshop. This guild system, while sometimes rigid, did help maintain standards and ensure the preservation of metallurgical knowledge. Guild regulations specified everything from the quality of materials to be used to the number of apprentices a master could train. In some cities, certain metalworking guilds became powerful economic and political forces, their members forming an important part of the urban middle class. Different regions of Europe developed specializations based on local resources and accumulated expertise. The forests of Central Europe provided charcoal for smelting, while rich iron ore deposits in places like Sweden, the Basque country, and various mountain regions supplied raw materials. Some areas became known for particular products. Sheffield in England for cutlery, Nuremberg in Germany for precision metalwork, the Basque region for high-quality iron. These regional reputations often lasted for centuries, built on generations of accumulated knowledge and refined technique. The production of steel remained challenging and expensive throughout much of the medieval period. European smiths typically worked with iron that contained varying amounts of carbon, learning through experience and careful observation how to recognize and work different grades of material. The process of carburization, heating iron in contact with carbon-rich materials to allow carbon to diffuse into the surface, was practiced widely, though the scientific principles underlying it remained mysterious. A skilled smith could judge the carbon content of a piece of metal by its color when heated, by the sparks it produced when struck against a grinding wheel, and by how it responded to quenching in water or oil. The medieval period also saw continued refinement in smelting techniques. Bloomery furnaces, the traditional method of producing iron, were gradually improved to run hotter and more efficiently. Some European regions began building taller furnaces that could operate continuously, fed from the top while slag was drawn off from the bottom. These improvements increased output and improved the quality of the iron produced, though they still fell short of the highly efficient blast furnace technology that had been developed in China centuries earlier. Specialized metalworking techniques flourished during these centuries. Armorers developed sophisticated methods for shaping plates of steel into fitted suits of armor, carefully hammering curved surfaces and creating articulated joints that allowed movement while providing protection. Bladesmiths refined their tempering techniques, learning to heat-treat different parts of a sword differently, leaving the spine somewhat softer and more flexible while making the edge very hard and capable of holding a sharp edge. Bell founders perfected the art of casting large bronze bells, calculating the proportions of copper and tin to produce specific tones, and developing the mold-making techniques necessary to create these sometimes enormous objects. The knowledge flowing along trade routes continued to influence European metalworking. Crusaders returning from the Middle East brought stories of Damascus steel and Wootz blades, inspiring European smiths to experiment with their own techniques. The specific methods of creating the legendary Eastern steels remained elusive, but the pursuit of similar quality drove innovation and experimentation across the continent. By the late medieval period, the stage was being set for new ways of thinking about metalworking. The accumulated practical knowledge of countless smiths represented an enormous body of expertise, all of it learned through apprenticeship and hands-on experience, preserved in workshop practices rather than written treatises. Yet some craftspeople and scholars were beginning to write down observations, to measure and record, to ask not just how to work metal, but why certain processes produced certain results. This gradual shift towards systematic investigation would eventually transform metallurgy from an ancient craft into a modern science, though that transformation still lay in the future as the medieval period drew to a close. As the medieval period drew to a close and Europe entered the age of the Renaissance, something remarkable began to happen in the workshops and universities across the continent. The ancient craft of metalworking, which had been passed from master to apprentice through demonstration and closely guarded secrets for thousands of years, started to transform into something new. It was becoming a subject of systematic inquiry, of written analysis, of scientific investigation. For millennia, metallurgists had worked by instinct and experience. They knew that certain ores produced better iron, that specific temperatures yielded stronger steel, that particular quenching techniques created harder edges. But they knew these things the way a cook knows a recipe, through repetition and tradition rather than through understanding the fundamental principles at work. The why remained hidden beneath the how. The transformation began quietly in the workshops of curious craftsmen who started keeping detailed written records of their experiments. In the early 16th century, a remarkable German scholar named Georgius Agricola began visiting mining operations and smelting works throughout Central Europe. Born in 1494, Agricola was trained as a physician, but his insatiable curiosity drew him to the underground world of mines and the fiery realm of furnaces. He spent years observing, questioning, and documenting everything he witnessed. In 1556, shortly after his death, Agricola's masterwork De Re Metallica was published. This beautiful volume, illustrated with detailed woodcuts, represented the first comprehensive attempt to systematically describe mining and metallurgical practices. Page after page revealed the secrets of the trade, how ore was identified, how furnaces were constructed, how metals were separated and refined. For the first time, the knowledge of metallurgy was being organized, categorized, and made available beyond the closed circles of guild craftsmen. The book showed cross-sections of mines with timber supports, workers operating bellows and tending furnaces, the tools used for each stage of production. It described different types of ores and how to recognize them, various furnace designs and their purposes, methods for testing metal quality. While Agricola did not yet understand the chemistry underlying these processes, his systematic documentation marked a crucial turning point from medieval craft to Renaissance science. As the 17th century unfolded, natural philosophers across Europe began applying new methods of inquiry to the material world. The the scientific revolution that transformed astronomy and physics gradually turned its attention to the nature of matter itself. What were metals made of? Why did they behave differently from one another? What happened during the mysterious transformations that occurred in the furnace? In England, Robert Boyle conducted careful experiments on the properties of metals, subjecting them to various tests and documenting the results with unprecedented precision. His 1661 work, The Skeptical Chemist, challenged ancient theories about the fundamental composition of matter and called for experimental evidence rather than received wisdom. Though Boyle could not yet explain what metals truly were at the atomic level, his insistence on empirical testing and reproducible results established principles that would guide future investigators. French scientist René-Antoine Ferchaud de Réaumur brought this experimental approach directly to the study of iron and steel in the early 18th century. His systematic investigations, published in 1722 as The Art of Converting Iron into Steel, represented perhaps the first truly scientific study of steelmaking. Réaumur conducted hundreds of experiments, carefully varying temperatures, times, and materials to understand what made good steel. He demonstrated that steel could be produced by adding something to iron, though he did not yet know it was carbon, and that cast iron could be converted to wrought iron by removing this same substance. Through meticulous observation, Réaumur identified different types of steel microstructures, though he could not yet see them under microscopes that were not yet powerful enough. He understood that slow cooling produced different properties than rapid quenching, and he developed improved methods for case-hardening iron by packing it with organic materials and heating it for extended periods. His work represented the marriage of practical metallurgy with systematic scientific method. As the 18th century progressed, chemists began to identify and isolate the various metallic elements. Swedish chemist Axel Fredrik Cronstedt isolated nickel in 1751 from a copper-colored ore that miners had previously dismissed. His countryman Carl Wilhelm Scheele discovered several elements, including manganese, in 1774, while the brilliant Swedish apothecary Torben Bergman developed systematic methods for analyzing mineral composition through wet chemical techniques. The gradual identification of elements revealed that metals were not simply variations of one fundamental metallic essence, as some ancient theories had proposed, but distinct substances with unique properties. Iron was iron, copper was copper, tin was tin, each with specific characteristics that could be measured and predicted. This understanding laid crucial groundwork for the eventual development of the periodic table and modern chemistry. In England, the clockmaker and scientific instrument maker John Smeaton applied engineering principles to metallurgical furnaces in the 1760s, conducting systematic experiments to improve blast furnace efficiency. He carefully measured fuel consumption, airflow, and metal output, treating the furnace as a machine that could be optimized through rational analysis rather than simply tradition and guesswork. French scientist Antoine Lavoisier's revolutionary work on combustion and the conservation of mass in the 1780s finally explained what happened when metals burned or rusted. His identification of oxygen and its role in forming metallic oxides solved mysteries that had puzzled metallurgists for thousands of years. The transformation of ore to metal was not mysterious magic, but a chemical reaction that could be understood and controlled. By the late 18th century, mineralogists were developing systematic methods for classifying ores and rocks. Abraham Gottlob Werner in Germany established principles of mineral identification based on observable characteristics. His students fanned out across Europe, bringing systematic geological and mineralogical knowledge to mining regions. The mysterious role of carbon in steelmaking became clearer through the work of several investigators. English scientist William Hyde Wollaston examined steel microstructures and suggested in the early 1800s that carbon content determined steel's properties. French metallurgist Pierre Berthier conducted chemical analyses that confirmed this hypothesis, finally explaining why different steel-making techniques produced different results. As the 18th century gave way to the 19th, metallurgy stood transformed. What had been craft wisdom accumulated over millennia was becoming systematic science. The stage was set for the Industrial Revolution in steel production that would soon follow. The ancient art had not been lost, but rather elevated. The practical knowledge of countless generations of metalworkers, now supplemented by theoretical understanding that would enable unprecedented innovations. In workshops and laboratories across Europe, investigators were learning to read the language of metals, to understand their inner nature, to predict their behavior. The furnaces still glowed as they had for thousands of years, but now their light illuminated not just metal, but knowledge itself. As the 18th century gave way to the 19th, the understanding of metals had progressed from the realm of ancient mystery into the domain of chemistry and systematic investigation. Yet for all this growing knowledge, steel remained an expensive material, produced in small quantities through labor-intensive methods. The world was on the cusp of transformation, waiting for innovations that would turn steel from a precious substance into the foundation of modern civilization. In the workshops and experimental furnaces scattered across Britain and Europe, craftsmen and inventors wrestled with a persistent challenge. The traditional methods of producing steel, whether through cementation or crucible techniques, yielded excellent quality, but only in modest amounts. A single crucible might hold perhaps 50 pounds of steel. For special tools, weapons, or precision instruments, this sufficed. But the expanding industrial world hungered for steel on an entirely different scale. Railways stretched across landscapes, requiring rails that could endure constant use. Bridges needed to span ever wider rivers. Ships demanded stronger hulls. The gap between what steel could offer and what could practically be produced had never been wider. The breakthrough arrived in a most unexpected manner through the work of Henry Bessemer, an English inventor whose previous endeavors had included improvements to pencil leads and a method for making gold paint. In the 1850s, while considering how to produce better artillery, Bessemer turned his attention to the fundamental problem of steel production. He envisioned something radical. Rather than carefully adding carbon to iron or slowly burning it out in a crucible, what if air itself could be forced through molten iron? The concept seemed almost absurd to experienced metallurgists. How could one possibly control such a violent process? Yet when Bessemer built his experimental converter in 1856, a pear-shaped vessel that could be tilted to pour its contents, something remarkable occurred. As compressed air blasted through the molten iron, the impurities burned away in a spectacular display of sparks and flame. The carbon in the iron combined with oxygen from the air, and the heat from this burning actually kept the metal molten without requiring additional fuel. In approximately 20 minutes, several tons of pig iron transformed into steel. The process was not perfect in its initial form. The violent oxidation removed too much carbon, and certain impurities proved stubborn. But Bessemer and others refined the technique, learning to add precisely measured amounts of carbon-rich material at the end of the blow to achieve the desired composition. The addition of Spiegeleisen, an alloy of iron and manganese, helped remove oxygen and improve the final steel's quality. The impact rippled outward like waves from a stone cast into still water. Steel that had cost £50 per ton could now be produced for £7. Within a few years, Bessemer converters operated across Britain, continental Europe, and the United States. The distinctive roar of the converter, its fountain of sparks visible through the night, became emblematic of industrial progress. Yet even as Bessemer's process revolutionized steel production, it possessed limitations. Iron ore containing significant phosphorus produced brittle, inferior steel through this method. Unfortunately, much of Europe's readily accessible iron ore, particularly in regions like Lorraine, contained these troublesome phosphorus compounds. A parallel innovation emerged to address different needs: the open hearth furnace, developed by Carl Wilhelm Siemens and Pierre-Emile Martin in the 1860s. The open hearth process proceeded more gently than the dramatic Bessemer converter. In a large, shallow hearth, pig iron and scrap steel melted together under carefully controlled heat. The process took hours rather than minutes, but this slower pace offered advantages. Metallurgists could test the molten steel during production, adjusting its composition to achieve precise specifications. The open hearth furnace could also utilize scrap steel, effectively recycling metal rather than requiring fresh ore for every batch. The Siemens-Martin furnace achieved its high temperatures through an ingenious regenerative system. Waste heat from the furnace preheated incoming air and fuel gas by passing through chambers filled with refractory bricks. As these bricks absorbed heat from exhaust gases, they became radiantly hot, then transferred this heat to fresh air flowing through them. By periodically reversing the flow, the system maintained temperatures sufficient to melt steel while using fuel efficiently. Together, these innovations opened floodgates that had constrained human ambition for millennia. The quantities of steel available increased, not incrementally, but exponentially. In 1870, the world produced approximately 500,000 tons of steel. By 1900, production exceeded 28 million tons. Numbers that would have been unimaginable to earlier generations became routine statistics. The consequences manifested everywhere. Railways knit continents together with steel rails that could endure the endless passage of locomotives. Previously, iron rails had worn out quickly, requiring constant replacement. Steel rails lasted decades. Bridges soared across obstacles that had formerly divided communities. The Brooklyn Bridge, completed in 1883, suspended its roadway from steel cables, each strand a triumph of industrial metallurgy. Buildings reached toward the sky in ways that stone and brick alone could never achieve. The supporting framework of steel allowed architects to envision structures of unprecedented height and grace. The Eiffel Tower, erected for the 1889 Paris Exposition, stood as perhaps the most visible celebration of the Steel Age, its latticed iron framework rising more than 1,000 feet above the city. Ships transformed as well. Wooden vessels gave way to steel hulls that could be built larger, stronger, and more reliably than anything crafted from timber. Steam engines required less fuel when freed from the task of pushing wooden hulls through water. The great ocean liners and naval vessels of the late 19th century embodied thousands of tons of steel plate, riveted and shaped into forms that could cross oceans. In workshops and factories, steel machinery replaced wooden mechanisms. Tools that had been forged individually by skilled craftsmen now rolled from production lines. Standardization became possible on scales that craft production could never achieve. A farmer in America might use a steel plow nearly identical to one employed in Russia, both products of industrial manufacturing. The innovations continued cascading forward. In the 1870s, Sidney Gilchrist Thomas and Percy Gilchrist developed a modification to the Bessemer process, lining the converter with basic refractory materials rather than acidic ones. This seemingly subtle change allowed the removal of phosphorus during the blow, making the vast phosphoric iron ore deposits of Europe suddenly valuable. Regions that had seemed metallurgically disadvantaged found themselves sitting atop resources now accessible to exploitation. As the 19th century drew toward its close, steel had completed a transformation that ancient metallurgists could scarcely have imagined. The material that had once been produced ounce by precious ounce in sealed crucibles now flowed in rivers of molten metal through industrial complexes that never cooled. The knowledge accumulated over thousands of years, from the first tentative experiments with iron bloom to the careful observations of carbon's effects, had finally yielded methods that made steel abundant. Yet even as this revolution in quantity unfolded, the fundamental principles remained rooted in discoveries made long ago. The importance of carbon content, the need for proper heating and cooling, the value of various alloying elements. These truths transcended the scale of production. Whether a metallurgist in ancient India carefully tended a crucible, or an industrial chemist monitored an open hearth furnace, they engaged with the same essential relationships between heat, metal, and transformation. As the great steel mills of the industrial age continued their work into the 20th century, metallurgists and scientists began to ask new questions about the materials that had served humanity for so many thousands of years. The mysteries of metal were no longer simply about how to make it stronger or more abundant, but about understanding its fundamental nature and pushing far beyond what ancient craftspeople could have imagined. In the early years of the 1900s, a problem emerged that would have seemed trivial to those who had spent millennia perfecting iron and steel. Kitchen knives rusted. Ship railings corroded in salt spray. Industrial equipment deteriorated when exposed to moisture and chemicals. For all its strength, steel remained vulnerable to its oldest enemy: oxidation. The same force that had turned iron ore into colored rocks in the earth millions of years before humans walked upon it. The solution came through patient experimentation with the elements that could be added to steel. Metallurgists had long known that different additions changed steel's properties, but in 1913, a British researcher named Harry Brearley discovered something remarkable while searching for a better material for gun barrels. By adding chromium to steel in sufficient quantities, along with a smaller amount of carbon, he created an alloy that resisted rust and corrosion in a way that ordinary steel never could. He had invented stainless steel, though the name would come later, and the world of metallurgy had entered a new era of designer metals, created not by accident, but by deliberate scientific planning. The peaceful applications of stainless steel spread quickly through society. Surgical instruments could now be truly clean and lasting. Kitchen sinks and cutlery would shine for decades. The gleaming surfaces of this new material became synonymous with modernity and cleanliness, adorning buildings and machinery throughout the industrialized world. While steel was being perfected, another ancient metal was finally yielding its secrets. Aluminum had been known as an element since the early 1800s, but extracting it from its ores proved extraordinarily difficult. For a time, aluminum was more precious than gold, and Napoleon III was said to have reserved aluminum plates and cutlery for his most honored dinner guests, while others used ordinary gold. The metal was light, resistant to corrosion, and potentially abundant, but it remained locked in its compounds, defying the traditional techniques of smelting that had worked for copper, iron, and so many other metals. The breakthrough came not from heat alone, but from electricity. In 1886, two inventors working independently on different continents, Charles Martin Hall in the United States and Paul Héroult in France, both discovered the same electrolytic process for extracting aluminum from alumina dissolved in molten cryolite. This technique, which came to be known as the Hall-Héroult process, finally made aluminum production practical and economical. Within a few decades, the metal that had once been more valuable than gold became commonplace, finding its way into everything from cooking foil to aircraft construction. The story of titanium followed a similar path of long awareness, followed by sudden accessibility. Known as an element since 1791, titanium remained a laboratory curiosity for more than a century. Its remarkable properties, stronger than steel yet much lighter, and extraordinarily resistant to corrosion, made it desirable. But extracting pure titanium from its ores proved even more challenging than aluminum production. Not until the 1940s did William Kroll develop a practical process for producing titanium metal in useful quantities, and even then, it remained expensive and difficult to work. Yet for applications where weight and corrosion resistance mattered most, aircraft frames, spacecraft components, and specialized equipment, titanium became invaluable. The 20th century saw metallurgy transform from an art and a craft into a precise science built on understanding the atomic structure of materials. Scientists discovered that the properties of metals depended not just on which elements they contained, but on how those atoms were arranged. The crystal structures within metals, the boundaries between grains, the presence of dislocations and impurities. All these microscopic features determined whether a piece of metal would be strong or weak, brittle or ductile, resistant or vulnerable. This understanding allowed the development of superalloys, complex mixtures of metals designed for extreme conditions. Turbine blades in jet engines now operate at temperatures that would melt the pure metals known to ancient smiths. Yet they maintain their strength and shape because of careful alloying with elements like nickel, cobalt, chromium, and rare additions that earlier metallurgists never encountered. These materials represent thousands of years of accumulated knowledge combined with modern scientific understanding. The ancient principles, however, never disappeared. The careful control of heating and cooling that bronze workers learned 4,000 years ago still matters in modern heat treatment. The understanding that adding specific materials in precise amounts changes properties, first discovered when tin met copper, continues in every modern alloy. The patience required to experiment, observe, and refine techniques remains essential, whether working in a Bronze Age workshop or a contemporary research laboratory. As we rest here in the quiet evening, considering this long journey from the first hammered copper beads to titanium spacecraft, we might reflect that metals surround us still in countless forms. The device playing these words likely contains dozens of different alloys, each chosen for specific properties. The buildings sheltering us stand on steel frames. The vehicles that move us combine aluminum, steel, and specialized alloys in carefully designed proportions. Even our bodies depend on metallic elements: iron in our blood, calcium in our bones, trace amounts of copper and zinc enabling essential processes. The story of metallurgy is ultimately a story of human curiosity and persistence. Each discovery built upon what came before, each generation of craftspeople and scientists adding their understanding to the accumulated knowledge. From the anonymous artisan who first noticed that certain rocks melted in a hot fire to produce copper, to the researchers developing new materials for technologies not yet imagined, the work continues in an unbroken chain across millennia. And perhaps there is something soothing in that continuity, in knowing that the same fundamental transformations that amazed our ancestors still proceed in furnaces and laboratories today. The metals we have drawn from the earth, shaped, combined, and perfected, have carried us from the simplest tools to the threshold of the stars. And the principles that guide this work remain rooted in patient observation, careful experimentation, and the timeless appeal of transforming raw materials into objects of utility and beauty. As you drift towards sleep, you might imagine the glow of a furnace, ancient or modern, the patient work of hands shaping metal, and the long chain of human knowledge that connects us to those first metallurgists who saw possibility in colored stones and had the curiosity to explore what fire might reveal within them. As we bring to a close our journey through the ancient art of metallurgy, from those first gleaming copper tools to the mighty secrets of steel that built civilizations, we hope these stories have gently carried you through the evening. Thank you for joining us on this peaceful exploration of humanity's timeless craft. If these calm adventures have brought you comfort, we'd love to have you with us again. Like, subscribe, and share your thoughts in the comments below to help other smart sleepers find their way to restful nights. And now, as the night deepens and your mind settles, we wish you the sweetest of dreams. Good night, fellow dreamer, and may your sleep be restful and your dreams be kind.